Is the fifth speaker here? Li Yihe Li from, okay. All right, let's get started. Good morning, everyone. Welcome to the domain-specific languages session. And I'm your session chair, Qirun Zhang from Georgia Tech. And this session will feature 5 interesting talks. Today, our first speaker is Chris, and he's going to talk to us about his work on decoupling data layout from bounding volume hierarchies. Chris, please. Thank you.
Okay. Hello, everyone. My name is Chris, and today I'll be talking, as you mentioned, about decoupling data layouts from bounding volume hierarchies. This is work done in collaboration with my colleague, AJ Root, and my esteemed advisor, Fred Zed. Okay, so BVHs are really indexes for speeding up spatial queries. Here we present a very simple scene consisting of 6 triangles, but notably these can range from millions to billions of primitives. And we have the following query we might want to speed up. Notice the ray in the lower left corner, and the question we might ask is, which triangles in the scene does the ray intersect? And there's a couple ways we can do this. Perhaps we store these triangles in a list naively, and we perform a ray triangle intersection test for each of these. But this approach has a drawback. No matter what the scene is, we always have to perform this ray triangle intersection test, which is relatively expensive for every triangle in the scene. And so one alternative approach to this is using an acceleration structure, aptly named the bounding volume hierarchy, which recursively partitions objects in a scene and often asymptotically reduces the amount of work a spatial query must perform. This is represented as a tree data structure where each node bounds or envelops its children. And so we can perform the same queries we did before. And so we start at the bounding volume named A. And we ask the question, does the ray intersect A? The answer clearly here is yes, so we'll recurse into each of its children. We'll start with the ray children, the bounding volume C. Here we see that clearly the ray does not intersect C, so actually we can skip any work within C, and we don't have to recurse to D or E at all. We continue this process until we get the same exact answer as before, but in a much more work-efficient manner. And so what we've seen is that, in fact, these BVHs are used in numerous domains for many different types of spatial queries. This includes ray tracing in hydrodynamics, closest point query for robotics, collision detection used in physical simulation, and neighbor search used in molecular simulation. And what we've also seen is that these physical representations of BVHs is quite extensive. So here we've provided the components to describe a single node of a BVH. Namely, we need some way to describe the leaf and its fields, the interior nodes in its fields, a way to discriminate these, and finally the bounding volume, which here we've chosen, we made a choice of bounding volume, namely an axis line bounding box, or AABV. And so one physical layout we might choose is the following, where we have a struct called node, and first we store a tag as 8 bits. We then store the axis line bounding box, and finally we store the union of the leaf and interior node. Where in the case of the leaf node, we have these wasted bits, or wasted space rather, because the leaf node is much smaller in size than the interior node. We can also choose the following representation, where instead we store the axis line bounding box first, and we store a single bit to represent the tag, because clearly there are only two different cases we have to distinguish. And so what I claim is there's many works that have actually done a really good job of describing these bit-precise level layouts to include bit stealing made legal for algebraic data types, and also Dargent for these records and sum types. And what we're actually interested in is not only these intranode or per-node optimizations, but also internode optimizations, or optimizations across collections of nodes. And so here we have a very naive pointer-based layout, where each interior node contains a machine pointer to its left and right children. And this is really nice for data structures that are often readily mutated and shared. However, what we've seen is that these BVHs remain relatively static, and thus there lies a lot of performance in thinking about more read-friendly data layouts. And so we can consider the following tree laid out in a pre-order traversal in a single contiguous array. And this gives us better locality first. And second, what we get is that because this is laid out in pre-order traversal, we don't actually just store an explicit index to the left child. This is known implicitly. It lives directly after the parent. We can also consider this alternative layout, where we now store fields in separate arrays, which really cater to these highly vectorized machines such as GPUs. And lastly, as I mentioned earlier, we have this wasted space in the leaf case, and we might consider a more space-efficient layout such as the following. Here we store interior nodes and leaf nodes in separate arrays, and we actually encode in the reference type which array to actually look up into. And when actually implementing a BVH, what we're trying to do is minimize two objectives. This is obviously the runtime performance of the spatial query. That's the entire point of BVHs. But we also want to minimize the memory footprint of the BVH itself as well. And the reason for this is that these can be run on these more memory-constrained architectures such as mobile devices. And so what this gives us is not a single optimal layout, but rather a Pareto frontier of layouts to explore. And so, for instance, a Pareto optimal layout, the objectives of what I claim here is that the objectives are dependent on three factors. This includes the algorithm, so collision detection or neighbor search perhaps. It includes, obviously, the machine you're running it on. And so, the Pareto optimal layout for an x86 CPU with SIMD instructions is going to look much different than one for a GPU. And finally, it's going to depend on the characteristics of your input data. A sparse and dense scene will likely have very different ideal layouts. And perhaps, if you're doing ray tracing, whether your arrays are coherent or incoherent are also going to be important in choosing a Pareto optimal layout. And so when we look at prior work that optimizes these BVHs, what we notice that each prior work is really focused on one point in this design space. So we can concretely consider work from folks behind Embry, which is an industry-level graphics rendering library. And they have this paper dedicated solely to optimizing ray tracing on x86 for densely packed hair. And here are two other works that are really focused on entirely different points or evaluation contexts. And if this still isn't convincing, we cite an entire collection of papers that emphasize the importance of optimizing the physical layouts of BVHs for different points in this design space. And so obviously one sub-goal of this work is really to design a language that can express many of these layout optimizations. But more importantly, what we want to do is get away from this traditional approach of every time you need to explore a new physical layout, you have to write the logical specification in the algorithm over and over again. And so we propose this decoupling, where one time the domain expert writes an algebraic data type for the BVH, as well as a set of traversal algorithms, and separately the performance engineer can provide different physical specifications to explore perhaps different evaluation contexts or different points on the Pareto frontier. Okay, and so we provide a very high-level system overview of what our work looks like. And so first, the application developer, as I mentioned earlier, writes a tree traversal algorithm and some algebraic data type. Separately, the performance engineer or perhaps an auto-scheduler will write the physical layout. These are passed into our compiler, where we specialize the physical layout for the given algorithm code and then perform some domain-specific optimizations. And finally, we generate code for three different targets: x86, NVIDIA, and ARM. And I think one of the really cool parts about this work is actually every tree traversal algorithm we use in this paper was automatically generated from Bonsai using high-level set queries. And if you're interested in this or in mechanization of pruning tree traversals, you should go see AJ's talk on Friday at 4:30 p.m. Okay, so now we'll talk about each of these components in a little bit more detail. So first, we need a way to actually specify a logical interface. And so we have this type BVH. And a key insight of this work is when we're when we're writing algorithms for spatial queries, we don't actually have to make any assumptions about the physical representation of the BVH. So here we specify a very simple ADT, or BVH as an ADT. And so we have the type AABB, which is represented as 2 points in space, the lower and upper corners. And then we have the BVH, which is a sum type, where either we have an interior node containing the bounding box, the left and right child, or we have a leaf node which also contains a bounding box, some number of primitives n, and the primitives themselves. We can then write algorithms with respect to this algebraic data type. Here we have a very simple closest hit ray tracing algorithm with some pruning in addition to it. And again, we're making no assumptions about how this BVH, how this algebraic data type is laid out in memory. Okay. The next part of this talk will talk about specifying the physical interface of the BVH implementation, focusing on our layout language. And so to introduce the constructs of the layout language, we'll build the layout from ground up. And here we begin by defining a layout called linear BVH, which currently only contains an array of triangles over which we'll construct the BVH nodes. And so the first construct we'll discuss is a group, and we'll do this by showing an example. Here we have a very simple group called G1 that has exactly 4 elements, and it's indexed by the value I. And each element in this group contains a field called A of type F32, followed by a field called B of type I8. And so when we look at I equals 0, we point to the first A and B. I equals 1 points to the second A and B, so on and so forth. We can also do the structure of arrays optimization, where we have 2 different groups with a single field, but share the same indexing value I. And finally, we can compose these groups to do more advanced optimizations, such as array of structure arrays. And so in our, returning to our original layout, what we're doing here is replacing 2 fields in our group, namely the bounding box and also the value n, which represents the number of triangles that this node contains. Okay, so the next construct we'll talk about is split. And simply put, a split is just a way to do safe union types. And I should say this is highly inspired by prior work, namely bit stealing made legal. And what we're saying here is that if n, the number of triangles, is greater than 0, this is a leaf node. And otherwise, if it's equal to 0, this is an interior node. And this is simply an invariant of BVHs. And the nice part about this is now we don't have to explicitly store any kind of discriminant or tag. We then place some fields in each of the cases of our split, but additionally we have this notion of derived fields. So derived fields don't actually store any bits. This is just a way to compute some information on the fly. And so the canonical example, as I had mentioned earlier, is that if we know this array is stored in pre-order traversal, left to right, we don't actually have to store an index, an explicit index to the left child. We know it always lives directly after the parent. And finally, we had 16 bits of padding so that every element in our group nodes is 4-byte aligned. And interesting, I think the interesting thing here is we've actually built a layout that is modulo a few small changes that we skipped for brevity. The one that's used in the physically based rendering textbook, which has been shown by the authors to be sufficient to render some of the largest scenes publicly available from Disney. Okay. What our claim is that, with a couple more constructors or operations that we don't show in this talk but are in our paper, this is actually sufficient to express many advanced layout optimizations used in real BVH applications. This includes things like bounding volume quantization, which trades off a more compact layout for less work efficiency during traversal, but is still functionally equivalent in the world of spatial queries. This includes sum of arrays, as depicted earlier, which is a way to more compactly store some types where each injection may have disparate sizes. And here we're seeing a trade-off of space for additional compute at runtime. And finally, we provide a way to forego storing redundant information that might be shared between a parent and its children, thus allowing optimizations such as shared slab, where only a subset of the slabs of a bounding volume need to be stored for each child. Okay. The final component that we're going to talk about today is actually, how do we automatically specialize the layout for the given traversal algorithm? And so we do this through a process that we denote as destructor specialization. And so on the left-hand side here, we have a subset of the closest hit ray tracing algorithm. And the question is, how do we actually specialize accessing the field called right for the interior node, which represents the right child? And on the right-hand side, we provide the layout. And so we do this through a very simple pathfinding algorithm, where we start off with a base case, which is the name of the layout, and we proceed until we actually reach the field called right in the layout. And so first we jump to the group called nodes, accessed by the value I. We then jump through the split to the interior case because the write lives in that case. And finally, we access a field called write as required. We do this for every different field that's actually used in the algorithm. And finally, we apply some domain-specific and common compiler optimizations such as DC and CSE. And we found that we get better performance than general-purpose compilers such as Clang because we can make some stronger assumptions we can make some stronger assumptions in our higher-level IR. Okay. Additionally, we also perform constructor specialization. I think that the main takeaway here is that not all layout optimizations we want to do are invertible. And also, we need some way to specialize the constructor code, which maps like a BVH from a naive layout to the specialized layout. I think this is really interesting too, and you should see the paper for more details or come talk to me after this. Okay, and so to demonstrate there's no overhead with our techniques, we compare against two state-of-the-art libraries. The first one is the fastest closest point in the West, where we compare the running time of closest point query across a number of different scenes. And the second one is flexible collision library, or FCL, and we compare in a similar manner for collision detection, but this time for a number of different layouts. And the only claim I'm making here is we're about parity in both cases, and the reason for this is honestly we just have a monomorphizing compiler, sorry. And thus we have no runtime overhead because of our work. Okay, and lastly, to show the utility of our work, we actually performed this large design space exploration for closest hit ray tracing algorithms. And so, again, the point we're trying to make here is we're not trying to explore a single optimal layout, but rather this Pareto frontier, minimizing the runtime of closest hit ray tracing, and also the memory footprint of the BVH we're using. And so we do this for 19 different layouts. This consists of realizing prior state-of-the-art optimizations, but also some minute changes, such as changing the alignment of specific groups elements. We do this across 7 different scenes, which ranges in sizes from thousands of triangles to tens of millions of triangles, 2 different ray distributions, both incoherent and coherent rays, and finally 3 different machines, x86 NVIDIA GPUs and ARM CPUs. And what we show is that indeed, empirically we show that Pareto optimal layouts are algorithm, machine, and data specific, and you should see the paper for details that actually back this up. And hopefully this is surprising no one. Okay, and I think, again, another really cool part about this work is we are able to rapidly explore novel layouts. So here we combine optimization techniques from 3 different works. Namely, we have the implicit indexing and bit sealing from the linear BVH that I showed earlier. We use a SnapGrid X10 quantization technique, or bounding volume quantization technique, from a paper that's optimizing molecular simulations. And we use this dequantization scheme from the Embry folks who had a paper on compressing leaf-based bounding volume hierarchies. And this gives us a novel layout that we denote as PBRTQ16. And perhaps we can look at a single point in this evaluation context, namely Lucy, which is 28 million triangles, run on x86, and using coherent or primary rays. And clearly, PBRTQ16 is on the Pareto frontier. And interestingly, it's about 5 times faster than the most space-efficient layout that we were exploring previously. And also uses about 2 times less memory than the fastest layout we were exploring previously. But most importantly, what we saw is that PBRTQ16 is Pareto optimal in 35 of the 42 different evaluation contexts we were looking at. And so I think the main takeaway that we're trying to get at here is that physical layouts are important for these acceleration structures when seeking peak performance. And we believe this decoupling of data layout optimizations is crucial for making performance engineering as productive as possible. Thank you.
Thank you. Yeah, we have 3 minutes for our question and answer.
Hey.
Hi, thank you for the talk.
Uh-huh.
So
I see the sort of set of expressible spatial layouts. I was wondering a little bit more about the algorithmic language and your ability to express some of the other Embry optimizations, like they do packet tracing, and
yes,
so they'll swap back and forth. Like, what are your thoughts on those sorts of constraints?
My thoughts are the algorithm side is very important too, and actually my colleague AJ Root is working on exactly this. So you should talk to AJ Root after this. So AJ Root, this is originally work done by AJ Root that I've kind of built upon. And he has this entire system for optimizing these spatial query programs that really is combining both data layout optimizations and what we call scheduling, which includes things like packet tracing. And I think what is really cool about this is we're composing both of these together. So Yeah, talk to AJ Root.
Very nice work. I'm curious of whether this has application to specifying file formats and network formats. Have you
Yes.
applied it there?
So we have two different approaches after this paper. Is one, we either convince everybody that BVHs are the only important data structures and everything should use BVHs. I failed to do that so far. The second option is to generalize this to all algebraic data types, and we are currently doing this right now to include file formats and network-like formats. But anything that can be represented as an algebraic data type hopefully can benefit from stuff like this.
Any more questions? All right, let's thank our speaker again.
Good luck. Oh, I need to give you this, right? Let's see. Tape still works.
That's yours. That's yours. Maybe. Is that okay? You think so?
Can you guys hear the mic?
Yes.
Yeah. Let's try again.
And today our second speaker is Samantha, and she's gonna talk to us about her work on contextual embeddings, implementing bound variables through instant resolution.
Is the mic okay now? Yep, perfect. Nice. Thank you for the introduction. Today, I plan to take you on a journey to explore a classical problem in programming languages, that of the syntactic representation of embedded languages with binders. Now, I'm sure that in the DSL session, I don't need to motivate why DSLs are so great and why we love them. We've just seen how great they can be with the previous talk. Now, my favorite flavor of DSLs is embedded DSLs, simply because I'm too lazy to do all of the work that goes into making standalone languages. Of particular interest today is the syntax of embedded languages with binders. That is, language constructs that close over or bind variables, such as let or lambda. So the canonical representation of syntax with binding is that of de Bruijn. This first-order representation has a lot of benefits. Firstly, it can be intrinsically typed. That is, we can embed a language such that the host type system will rule out ill-typed guest terms, such as the duplicator term here if you're embedding the simply typed lambda calculus. Another desirable benefit of embedded languages is metaprogramming, the ability for the host language to inspect, construct, optimize, and analyze programs of the guest language. With this representation of syntax, the whole AST is accessible without restriction. In fact, this representation is so amenable that the notion of unembedding has come about, and that is where you convert from some representation to this representation, because we like it so much. Unfortunately, this representation is not very ergonomic to use. It's really easy for a user to write the wrong term, for example, mixing up TT and FF here. And that is the crux of our quest here. We want a syntactic representation that has all of these qualities and more. We present contextual embeddings. A contextual embedding is a technique for embedding languages with binders that combines the benefits of the first-order representation with an ergonomic interface, even working for modal and substructural type systems, and contextual embeddings are isomorphic to the first-order representation via a type-safe unembedding, something that has eluded the community thus far. But why has it eluded the community? Well, we are just one part of the heroic quest for the golden binder representation, or as I like to call it, the Hodyssey. Allow me to bring you up to speed. So our heroes set sail with the idea of higher order abstract syntax, or HOAS. So here is the simply typed lambda calculus represented using HOAS. So HOAS represents guest binders with host binders. Notice how lam here is taking a host function and the lack of a var constructor. This allows us to write guest terms really ergonomically, utilizing the host binding infrastructure. And this is easy for both users and implementers alike. Now our heroes are going to encounter a number of problems on their journey. The first of which is a lack of decorum. Our heroes find the need to formalize their syntax in a theorem prover. Alas, theorem provers only support strictly positive types. This means that our HOAS representation would be rejected due to the negative occurrence of HOAS highlighted here in yellow. Fear not, though. Our heroes, Desperu and Hershowitz, stepped up to save the quest. Their solution, weak HOAS, is to have a separate type for variables var. Now, where formerly there was a negative occurrence of the type we are defining, we just have a separate type, which is accepted by theorem provers. Next, our heroes were blown wildly off course. Oh no. Blown all the way to their next encounter, the seductive siren of exotic terms. An exotic term is a term of the embedded language that does not correspond to an expressible term of the guest language. For example, here, because our host Haskell supports pattern matching, we can branch based on the name of the variable, which is not something that is expressible in the simply typed lambda calculus. Luckily, Chapala marshaled the different talents of his companions, combining weak HOAS with ideas from Washburn and Weyrich, harnessing the power of parametric polymorphism to banish exotic terms, creating FOAS. The key development here is to be parametric over V. This excludes exotic terms because you cannot match on an abstract type. In fact, this combination kills two birds with one stone. Washburn and Weyrich present kata, effectively a fold, as a convenient elimination form for HOAS terms. And this is a really useful development until you want to perform operations that require more than one traversal of the syntax tree, or as I like to call them, superfold semantics, as we're going to encounter with our next challenge. So consider writing an optimization function for your embedded syntax. Optimizations require more than one traversal of syntax, because performing one operation might lead to opportunities for further optimizations. So you want to traverse the syntax tree more than once. So kata is not going to cut it here. Luckily for us, a clever choice of V with our FOAS allows us to unembed to our lovely first-order representation. So unembedding to the first-order representation grants us its amenability, allowing us to reuse existing de Bruijn optimizations to perform our optimization as desired, because it's not limited to one traversal of syntax. Alas, there are still issues. Our quest is not over. Our heroes are now stranded on the Isle of Calypso with their onboard computer lost. So they need to transmit their code for execution elsewhere. Now, unembedding allows them to remove host closures, making the code transmittable, but there's no way to convert it back at the other side. We need a way to unembed. This time, Atke et al. Saved the day by proving the first order and higher order representations to be isomorphic. And they used this proof to justify an implementation of this isomorphism, providing us with the desired there and back again functions. However, all current implementations of unembed rely on external justifications, like Atke's paper-long proof, to implement it using unsafe operations like the unsafe coerces shown here. And that's where our hero's journey ends, stranded with this unsatisfying reliance on external justifications. 17 years have now passed. And this is where I come in. Our ICFP 23 paper, Embedding by Unembedding, realizes the full potential of unembedding, showing it to be invaluable when defining languages with interesting semantics, such as those in the bidirectional or incremental domains. But it still relies on those external proofs. And that brings us up to right now, with me telling you this story and the elusive type-safe unembedding still at large. Now, host languages have developed and become a lot more powerful in the past 17 years. So motivated by this and my work on the embedding by unembedding paper, I thought it was time again to pick up the quest for the golden binder representation, resulting in contextual embeddings, complete with a type-safe unembedding, an ergonomic interface, and more. The secret to our success? Well, type-level programming of host language is much more powerful. In particular, the type class resolution has become a lot more expressive. We combine this with the observation that the difference in size between the bind site context and the use site context of a variable is precisely its de Bruijn index. Let me show you a quick example. Here's the const function. So for the variable x, at bind site, the context only contains one variable, x. At use site, the context has grown to size 2 to include y. And I'm sure here at PLDI, you need no convincing that 2 minus 1 is 1, the desired de Bruijn index as desired. Now, let's dig into the details of contextual embeddings. Where previous approaches start from HOAS, we're going to preserve the context so that we can make use of our observation, and we're going to start from the de Bruijn representation to construct our solution. So here is an embedding of the STLC in Haskell using the de Bruijn first-order representation, where we have taken care to ensure that it is intrinsically typed. So we're going to define our guess types and the typing context as Haskell data types with the plan to lift these to the type level. So our guess types, the types of the simply typed lambda calculus, can be unit or function types, and the typing context is a snocked list of guess types. For the de Bruijn indices, to ensure intrinsic typing, we enrich the standard natural number representation with type information to ensure that the indices actually refer to a type in the context. These enriched de Bruijn indices are parameterized by the typing context and the type of interest. Top indicates that the type we are referring to, T, is at the top of the context. And pop indicates that the type we're referring to is deeper. So T prime is not who we are looking for here, so we're going to pop them off and continue looking for T inside T's. These pieces come together to define our syntax. Guess terms are also parameterized by typing context and their guess type. Variables use the de Bruijn index. Lambda abstracts over a body term in an extended context, T's snock T1, to introduce a function of type T1 to T2. An application is about what you would expect. Starting from this de Bruijn representation, we change lambda to use a host function, because this is great for ergonomics. Of course, as we learned on the Odyssey, this introduces an exotic term, because now you can match on the index. To fix this, we replace the index type with a truncated index type called proxy top, which is just the index type with only the top constructor. Because there's only one constructor, there's nothing to branch on, preventing exotic terms. It's useful to think of the value of type proxy top as a capability, a piece of data that gives us access to the most recently bound variable of type T. But how do you access previously bound variables? To access all previously bound variables, and not just the most recent, we introduce a type, reify index E. This type is evidence that T's2 is an extension of the context T's. This, and our observation about bind and use site contexts, can guide a function reify to turn a proxy top T's T into an index T's2 T. However, de Bruijn indices are back. Providing reify index E is just the same as providing the de Bruijn index. Fear not, though, this is where we make use of the host's instance resolution to construct this value for us. By swapping reify index E out for a type class with a reify method, we can remove the user's need to provide this evidence. It can be done automatically with the following instances. The first instance, corresponding to the refl constructor, is where both typing contexts are the same, offering a straightforward transformation from proxy top to top. The second instance corresponds to the step constructor, and it's a little bit more involved. It says, to evidence that T's3 is an extension of T's, we require that T's2 is some extension of T's, and that T's3 is exactly T's2 extended with one more type, A. Reify is then recursively defined, with the highlighted constraint asserting that the recursive call exists, and then to account for that final difference, the addition of A, we add a pop. Essentially, we are counting the difference between the bind and use site context to produce the correct de Bruijn index. Et voila! Here is the full type system. Notice how reify index E has been replaced with a type class constraint. And it all, just about, fits on one slide. Let's review the key points. By using host functions, we have achieved the same ergonomics as HOS. The singleton proxy top allows us to snapshot the context at bind site. And this gives us just enough information to calculate the correct de Bruijn index at use site automatically using the host's type class system. Let's review contextual embedding against the criteria that we've gathered across our journey. Firstly, they are intrinsically typed. The host type system is going to reject ill-typed guess terms. Our host functions make guess binders ergonomic. We made sure that our embedding is strictly positive. By preserving the typing context, it is much easier than previous work for a contextual embedding to be proved isomorphic to the first order embedding, and this provides a number of benefits. It ensures that there are no exotic terms. We can define a type-safe unembedding without relying on unsafe operations, axioms, or external arguments. Notice here there's no unsafe coercers to be seen. We also have an inverse to unembedding, contextualize. And we support superfold semantics, so you can unembed, operate on the amenable first-order representation, and convert back using contextualize. Finally, because our technique for managing binders is agnostic to the type setting, it can be used to embed languages with modal and substructural type systems, even if the host does not have such a type system. Please see our paper for example embeddings of the Fitch-style modal lambda calculus and the linear lambda calculus. Yay! Oh, that's not the end. That's not the end. It was just a yay. So we recommend this technique if you want to embed a language with binders, where you need more control over the syntax than HOS allows. For example, you need superfold semantics. So if you're considering using a contextual embedding, which I hope you all are, you all applauded, so you must be, you need a host that supports JDTs, type-level data, so this is the data kinds extension in Haskell, and has a suitable type class system. The key mechanism that is required is the ability to select instances based on type equality. Our reusable artifact has implementations in Lean and Agda, and I encourage you to take a look. You can also rest easy that contextual embeddings won't blow up your machine with overheads. It does come with run and compile time overheads, but we think that they are reasonable. And your embedding will also enjoy all the benefits you know and love of embedded languages. Terms can be written compositionally, so you can define smart constructors like lam2. Also, the intrinsic typing grants type inference, and in fact, this infers the most general type. We also found that our error messages are quite readable. For example, consider ill-typed K. The error message tells us exactly what is going on. In summary, we have advanced the quest for the golden binder representation. To tackle the hard problem of syntax with bindings, we present contextual embeddings. They use the host's instance resolution mechanism to automatically calculate the correct de Bruijn index, allowing for a type-safe, ergonomic, and flexible embedding. Of course, though, the quest is not over. We have not yet reached Ithaca. It's an odyssey. This is not the end of the story. At Bristol, we're starting a large project based on the ideas here, recruiting PhDs and postdocs. So stay tuned and consider joining us. If you're interested, speak to me or email Mung. And of course, I encourage you to read the paper. Thank you for listening.
Thank you for the talk, and we have 3 minutes for Q&A.
Thank you for that lovely talk. So I was going to ask about substructural type systems. We already dealt with that. But what about polyadic or sort of variadic binding, like where you had like a multi-lambda or something like that? Have you tried these kind of or maybe like a
match?
Match on
Match,
pairs.
yeah, so match is fine as well.
Yeah.
The proxy top just extends the context twice.
Okay, so you can just kind of use it twice, basically.
Yep. In our artifact, we have examples of match.
Nice.
Yeah.
Cool. Great.
Any more questions from the audience? I have a quick question. So for your new DSL, have you done any user studies and to see how the developers perspectives on your new language in terms of making fewer errors and be more productive, things like that?
No, unfortunately, we have not done a user study, but we definitely should.
Okay, yeah, thank you. Any more questions?
Awesome talk. If this is so good, what do you think is left that you haven't done yet that's further on the quest?
So we currently have someone working on making a quantum language doing this. And we have someone else benchmarking this against the Popplemark challenge. So that's a nice way of evaluating how things work with binders. So we're going to use that to inform future directions. So results incoming.
All right, let's thank our speaker again.
You might need more tape. Oh, yes. Sorry. Sorry.
All right, now we are ready for the third speaker. Our third speaker is Ritvik, and who is gonna talk to us about his work on code constraint optimization with tensor networks.
Solve constraint optimization problems with tensor networks, as Chiran mentioned. This work was done with our collaborators, Chengpeng at Slack, who is a great resource in understanding quantum simulation problems and how tensor networks work, Siddharth Dangwal at UChicago, and of course my advisor, Professor Sarah Chor at Stanford. In this talk, I'll be focusing on optimization problems that are formulated over discrete variables, where you have an energy function that is described in terms of what is called a Hamiltonian. This is a popular formulation often used in quantum systems, where you want to simulate and understand some chemical or physical phenomena. And it's used in other domains like Ising models or combinatorial optimization. In this setting, the overall task that you have at hand is the following. You want to find an eigenvector of the Hamiltonian matrix that has the smallest eigenvalue. This minimal eigenvalue is just the ground state energy of your system. For many of these problems, the Hamiltonian matrix and vectors that describe states can become extremely large. That is why domain specialists in quantum simulation often represent the Hamiltonian and state vectors as a product of smaller tensors. Various tensor network algorithms exist that allow you to work on solving these optimization problems while working with this factored representation at hand. Often these optimization problems, however, have a lot of implicit constraints, and frameworks and solvers for tensor networks don't often provide you first-class supports for working with these constraints. Users often end up having to manually implement these constraints themselves in the solver on how they implement the tensor network or how they encode the Hamiltonian itself. And that is what we found while talking to experts in this area. In this work, we present our DSL mask that allows you to describe such optimization problems with first-class support for expressing and efficiently using constraints. These programs can be compiled to tensor networks with our compiler, and the compiled code uses existing tensor network libraries and solvers to solve the problem at hand. So let me first lay out an example of what kind of problems are we actually interested in here, and I'll use this opportunity to explain our DSL2. Starting off, you want to find the lowest energy configuration of a quantum system. It has 4 variables. Since it's quantum, all 4 variables, for now, we can assume that they map to 4 nodes, and each of these nodes can live in superposition of one of 2 states, red or blue, and state 1 or 0 respectively. We have 4 variables, so 2 to the power 4 possible states, or 16 states in total. We represent these variables in mask as this qvars object, which has size n equal to 4, each with d equal to 2 states. Note that we can support higher order systems as well, which is actually very common in this domain, especially used by physics simulation folks. The Hamiltonian for such problems is often defined piecewise in broken up pieces that applies local operations. In this case, it will apply an operation that will flip the color of a node if it has 2 blue neighbors. I'll first define some helper matrices that will help us describe this exact operation. You have a matrix that allows you to select your neighbor being blue or in state 0. You have one to encode the blue to red transition, and so on. You can compose them together by doing tensor products to form the overall local transition operation, and then apply them to variables 1 to 3 and 2 to 4 separately, implementing the overall Hamiltonian of the system right here. So now, in this case, I can solve this problem exactly, actually. I'll build up the full exponential sized Hamiltonian. I'll find the eigenvector that has the smallest eigenvalue. It is this sparse vector that has 3 non-zeros that I've highlighted here. It's often written in quantum notation like I've shown right here. We don't need to understand the notation for this talk. Just assume that this solution means you'll see the variables to be in all blue configuration for 50% of the time, and the second and the third node will be observed to be in red state 25% of the time each. However, this way of solving this problem was never tractable because of the exponential scaling. That is where tensor networks come in. A compiler in this case will use an iterative algorithm that will take your quantum state S, apply an operation on it, which is a function of the Hamiltonian, and give you the next state Si plus 1. All of these 3 things have to be implemented as tensor networks in this problem, and you want to slowly converge the quantum state to the ground state. The result of this algorithm can be seen as this heat map. This just visualizes the probabilities of each state across all iterations with the weights shown right here. To see if it works, we can just see at the very end, you'll see around 0.5 weight of the heat map for all blues, and around 0.25 color for the second or the third node being red. At start of this algorithm, of course, we started in a uniform mix or superposition of all states, and we can mark positions whenever we get within a certain percentage error from the solution. So at 97th iteration, we are at like around 10% error. Now, where do constraints in this problem come in? Well, constraints in these kinds of problems can come from the Hamiltonian itself. For example, in this case, if you had all blue nodes, you have 2 possible transitions. But if you had no node that has 2 blue neighbors, no transition can take place. In fact, these kind of states will have restricted dynamics. You can't really go from all states to all states at all points of time. And this is what domain specialists often exploit. For example, in this case, they'll rule out configurations that have any red-red combination that they can find. So how would those constraints be encoded? Well, one very general way would be to modify the Hamiltonian by doing regularization, which is adding some penalty terms on your energy function, artificially inflating their energy. In mask, this can be represented by adding a few lines of code that penalizes these states. On the other hand, what we can do is prune out or zero out these states that are invalid explicitly by changing the tensor network itself so that these states never show up. In mask, this is represented as the simple constraint add syntax that rules out the red-red or the 1-1 configuration that I was talking about. Here's the result of a 3-way comparison. Here's the result for unconstrained solution first. We get to 10% error in 97 iterations. With regularization, we get to the same point in just 78 iterations because invalid states have been suppressed. Or you can zero them out, in which case you'll get to the same solution in only 68 iterations. In fact, if I plot the error of all these 3 points across all 150 iterations, you'll find removing these states actually results in best solution quality at all times. So how can we impose these constraints? Our compiler takes advantage of the fact that to constrain a quantum state, what you basically want to do is you want to take this vector that I've denoted out with all the names for all states, and you want to just prune out anything that has RR word in it. So you want to zero out these points that I've mentioned here. This can be basically done with tensor algebra with a sparse matrix that has non-zeros at valid points and zeros on invalid combinations. But this matrix itself is exponential in the number of variables. So again, it needs to be implemented as a tensor network. So for the constraint at hand, we'll take a look at the mask code. We'll extract out the constraint. It's this constraint that we call not equals constraint. In this case, what happens is this constraint basically says, I have a bunch of quantum variables. They explicitly cannot be in the state written on the right. That is, the probability associated with this state is 0. And they can take any other quantum state, whatever they want, in the optic process. To compile this constraint, we basically need two properties. We want to enforce this constraint locally. And in this case, it needs to be the way this constraint is implemented is we only want to accept and reject state combinations. This will allow us to build a tensor network where each variable will get its corresponding tensor, and it can communicate with its neighbors. Xi can communicate with xi minus 1 and xi plus 1. Turns out this problem is pretty straightforward to solve because you can build a step-dependent discrete finite automata that will implement exactly that same constraint and can be mapped to a tensor network. Notionally speaking, what that means is each DFA iteration here will become a tensor in the network that I'll be talking about soon, and all transitions in this DFA will be non-zeros in the sparse tensors that get generated. For our example at hand, building a DFA could be very straightforward. You can have two states, one that says, oh, my left-hand side did not match right-hand side, that's the accepting state. Or I can have the scenario, my left-hand side did match the right-hand side, that's the state we want to reject when this DFA is done. So the transitions for this could be the following. At step I, if you're in state 0, the constraint's basically already satisfied. You can stay there however long you want. If you are in state 1 and you find a mismatch, you can switch over your DFA states. Or in the case where you are in state 1 and you've again found a match, in this iteration as well, you'll stay in state 1. Now, how does a tensor come out of it? Well, at any variable, let's take the first variable for this. We have some types of transitions that are valid on your DFA. We'll start in state 1, so there's these two types of transitions. I'll build this three-dimensional tensor where there's this index Bn that carries the DFA state after the current iteration will complete. So we can denote out the non-zeros of this tensor by a truth table where I'll just show the non-zero elements. First, we have a transition switching over from state 1 to state 0 whenever xn was not equal to wn. Well, that's just a non-zero that just says we have non-zero elements in this tensor whenever xn wasn't equal to wn and bn was 0. That is the state of the DFA after this was 0. Similarly, you can have the transition of staying in state 1 if xn matched wn. There's one other type of transitions that can show up, and those are like transitions that are explicitly not defined on our DFA. For the last variable, you have a scenario where you've matched up till now, and you explicitly want to rule out the final configuration, that is, we've matched after the DFA is complete. We write it out or express it as an invalid transition, which becomes a 0 element in the truth table, shown with the value right there and highlighted in red. So a lot of our constraints can be implemented to a tensor network through this process. There's this one other type of constraint that I'm not talking about here in this talk. Please refer to that for the paper, which can be directly implemented to a tensor network and doesn't really go through this DFA process overall. For details and proofs for some of these transitions that I've talked about and these mappings that I was talking about, please again refer to the paper. Overall, this gets us to go from a land where original constraint implementations working in this particular domain either required users to define or change how the tensor network would work with quantum number constraints, or was implemented explicitly as one-off implementations for these three kinds of constraints I show right here. And sometimes some constraints weren't even supported. The only way you could encode them out was regularization or penalization, because that's the most straightforward way one could do this. On the other hand, Cotton allows you to generalize various constraint implementations here to a larger family of constraint expressions that we can support. Now, I can talk about how these constraint encodings improve the efficiency of tensor network algorithms and result in great performance, especially when compared to the only other general scheme we could find, which is always using regularization. For this, we'll evaluate over 2 physics benchmarks called KL and PXP right here. We don't really need to understand what the physics underneath is. And just note that they're solved, again, using an iterative tensor network algorithm. So, and I would like to obviously thank Aaron Sass at Google and Shengtao Jiang at Stanford for helping us source and understanding these benchmarks, and other specialists we worked with and talked to. We run each model for different number of variables, n, and variable encoding d. These were points I mentioned at the start of this talk as things we can control on the mask code itself, and then also modulate another parameter called bond dimension. I haven't talked about it much. You can just think of it as a proxy for model accuracy. The higher it is, the more accurate your final solution will be. We'll evaluate constraint encodings to see how it will improve DMRG convergence. To do that, we'll first evaluate our projection-based tensor network, get its final solution, use it as a target for the regularization-based run. Again, the only other general way to do this. We'll run each evaluation setting with different starting seeds. We'll then report the average reduction in number of iterations and the average simulation speedup with the minimum and maximum speedup as well that we saw across these 5 runs. I call it a simulation speedup because Julia has JIT, and we want to exclude the overheads that can come up, especially on smaller models when you're JITting a bunch of code. Here's the result. But before we dive into what the results actually mean, let me just explain how to read this plot. You have different number of variables in these different groups. In each group, we're changing the bond dimension, increasing it from 10 to 80, I think, in this case. And that's just basically increasing the solution quality as you go from left to right, making it harder and harder. Next, for our speedups, I'll show the average in this bar chart right here. And I'll show these markers to show the minimum and maximum speedup we saw across all the 5 runs. Here's our result for the Kitaev ladder D equal to 2 encoding. Just note that we generally see improving performance as number of variables increase or the bond dimension increases. This results in an overall reduction in iterations from around 8.7x to 59.5x. This roughly translates similarly to speedup from going from around 4.8x to 59.3x approximately. Then we tried a D equal to 3 encoding. Note, I told you all these quantum systems can often be evaluated for higher order systems as well. And this is one example where we are increasing the value of D. And overall, again, you see the same trend. Performance improves as you increase n and bond dimension. Here, the number of iterations goes down by around 5.1x to 21.3x. And that results in a simulation speedup of approximately going from 2.3 to 6.6x. Next, we evaluated a separate physics model. In this model, the task of interest for domain experts was to find the ground state of the system and then the first excited state and measure what the energy gap between these transitions is. I'll report the number of iterations for this ground state and excited state search on the left and the result corresponding to speedup on the right cumulatively. Again, you'll see improving lines or improving bars as you increase bond dimension or solution quality. Overall, the number of iterations goes down from 10.4x to 16.7x for ground state search. For the excited state search, that goes around from 9.1x to 10x. In terms of simulation speedup, we find an overall speedup of around 6.4x to 8.6x. Overall, we find that various physics benchmarks have, especially which have these Hamiltonian-based optimization problems, have these implicit constraints. Our work enables separating these constraints out from the optimization problem at hand. Then we can compile them completely separately to a tensor network supporting these constraints, allowing us to generalize to various other forms of constraints that hadn't been implemented before. These compiled constraint implementations can also provide you large speedups over regularization in particular, which is the only other general way to handle these things. We are currently working on building a benchmark set for these optimization problems. We are building improved tensor network implementations with specialized tensor algebra kernels that are particularly suited for working with Kotlin-generated tensor networks. In general, while working on this project, one thing I found was domain specialists often have very interesting problems and very novel solutions of how they want to solve them. Tensor networks in particular, working on quantum simulation, seemed to be a very cool approach to me. And one thing I started thinking of when I started this project was how can I make their lives better, improve these tools in the first place, but what other problems can they be generalized to? What other problems exist that are amenable to solving in the same format? At this point, that's the end of my talk. I would love to take any questions. And also here's a link to my paper, by the way. But yeah.
Thank you for the talk. We have 3 minutes for Q&A.
Hello, thank you for the talk. I have a question, which is, are the tensor networks generated by your approach, do you have any argument to their optimality or like any empirical results on that?
Thank you. That's a good question. So I think the question is basically asking, do we have previous implementations that we can compare to, or how good they are? The reason that's a good question is sadly because all of this work by domain specialists in this area is often just published in like these physics conferences or physics journals. Many of them don't have implemented code that you can like find or access to. I've worked with people who helped me source these problems, told me how they don't have access to this code anymore. They've lost it somewhere 2 years ago or something like that. So that was like one big trouble in comparing a handwritten implementation that they did to an implementation that we had. I had one anecdotal example though for the PXP model in particular. We had a implementation hand done by one person from Stanford who actually used regularization for imposing their constraints. And after a few quick conversations, we realized that for the particular encoding choice that they used, you could have implemented the same constraint that we are talking about right here. They knew how to do it for a smaller encoding. They didn't know how to do it, or they hadn't done it for a higher encoding, and they'd just given up on it. And they're like, oh, this performance seems fine to me. So that was like one anecdotal example that we found, like, okay, we have some code and we can compare against it. And those results will basically look like the PXP results I talked about, because that was basically their implementation then.
Hello. Hi.
Hello.
I'm Elam from MIT. I'm curious, in a lot of kind of continuous iterative optimization problems, sometimes you can actually get faster convergence, at least in the number of iterations, by overshooting or letting the constraints be violated, at least in the initial parts. If you think about like simulated annealing or KL annealing in training VAEs or something. So I'm kind of curious if you found, or if you have some intuition for why categorically preventing constraints from being violated, especially in early iterations, allows you to converge faster.
That's a good point. That's actually a good question, and that gets to like where these constraints actually come from as well in some of these cases. Adding constraints, especially at the start, can slow down your system, especially when you're doing regularization. But funny thing is, some of these constraints are not just for finding ground state more efficiently. Sometimes they're more like tools to search for some kind of solution that some domain expert is interested in. For example, this Kitev ladder example, the KL example I was talking about, there's the constraint basically there says that if you can swap a parameter around, you can, instead of converging to the ground state, can converge to the first excited state or the second excited state. And you can search what the overall phase diagrams or what these material properties will look like. And the problem becomes, if you're just trying to solve for, if you do that, you end up violating those constraints entirely, and then you have a solution that looks good, but is not the target that you were looking for in the first place. So these often also end up becoming just exploration tools. In this talk right now, I only focused on finding the solution or just the ground state, but in reality, the first experiment we showed was basically finding some excited state of the system. And we also like show how the solution quality that you get out of this for a tensor network is actually better and has lower errors and a better approximation quality that one could look at in the paper if they're interested in. Yeah.
All right, let's thank our speaker again.
Oh, thank you.
It's the tape. Let me this change the bit. Cool. All right, we are ready for our fourth speaker, Aditya, Siddhartha, sorry, yeah, who's gonna talk to us about his work on diagramming program values by spatial refinement.
Hi, yeah, can you hear me? Awesome. Okay, say I'm working with a binary decision diagram library in Python. I build a BDD for some formula, and I want to understand its shape. I'm in the REPL, so I do the standard thing. I print it, and I get this. Now, anybody who's worked with sort of any interesting data structure, matrices, trees, BDDs, knows this isn't super useful. To make any sense of it, I have to grab a pen and paper, squint at all those nested constructors, and start drawing. What would really help me if I could see something like this. The same Python value drawn the way we think of BDDs. Nodes layered and grouped by variables, distinct high and low edges, shared terminals. I mean, they're called binary decision diagrams after all, right? So why can't I do this every time I want to inspect a value? Because the usual way we get a picture is writing drawing code. Before the picture can tell you anything, you have to choose marks, compute positions, handle updates, basically manage a pile of rendering mechanics. A tiny amount of anything you write will actually capture BDD conventions. Most of it is just scaffolding. This talk is about Spatial, a language designed to tackle this problem. The goal of this work is for diagrams to be as cheap as printing. Every time you inspect a value, at the REPL, in a debugger, printf, whatever, you should have the option of seeing a diagram. And I don't think I have to convince anyone here this is obviously a PL problem, right? Expressing diagramming in terms of a language, and you can get a lot of important properties by design, right? The diagram is guaranteed faithful to the value being inspected. You wouldn't want your REPL output to lie to you. And when a diagram cannot be generated, the failure is semantic and can be explained in terms of your value. Let's go back to the BDD REPL output. The first thing I want you to see is that there's already a diagram here. All the atoms in the REPL output, basically constructor terms, ints, and strings, are nodes, and the fields, node ID, high and low, are edges. And once we add some quality of life improvements like deduplicating things and coloring by types by color, you get something like this. This is what Spatial reconstructs for you for free. No drawing code, no annotations, nothing. Every box is an atom of the value. Every arrow is a field. The problem is, this isn't the picture you want to see for a BDD, right? But with a little refinement, it can be. First, hide implementation details you don't care about, like node IDs and the none type. Then, arrange nodes so that parents sit above children. Horizontally align nodes that test the same variable and group by those variables. All right. And if you want a little visual zhuzh, distinguish nodes and edges by color and styling, and that's the diagram from the start of the talk. We didn't write any rendering code. We just specified how it should be arranged. So that's the workflow end to end. Start with a fateful graph, write some rules to refine it. When it's good enough for your purposes, stop. Basically, you want something that's useful, not necessarily pretty. I call this diagramming by refinement. To paraphrase Michelangelo, David was already in the marble, the BDD is already in the diagram graph. It's all there. And the nice thing is, it's not just a picture. This is this way. Yeah, in this video, dragging things around is generally useful when you're exploring a value. In this video, I'm trying to basically move nodes around. I cannot, as long as where I drag the node doesn't violate my diagramming rules, I'm good. The moment I try to violate any of the rules I've placed, I can't do it. You get this constraint interaction for free since you already told me how things should be arranged, right? So basically you get an interactive diagram for free. So what's the vocabulary you can really use to express all of this? Spatial is deliberately really small, and it's divided into two parts. One family of rules describes how things should be laid out. You've already seen some of these, hiding, orientation, alignment, grouping. And the second family describes how things should be drawn. That's things like icons, colors, visibility. The visual zhuzh I mentioned earlier comes from these. No new spatial meaning, just makes things a little easier to read. And every rule operates over selectors, which are relational expressions that pick out which part of a graph the rule applies to. So that's the language. You might immediately wonder, how did we hit upon this design? You probably have several other questions people have about DSLs. Is it expressive enough? Is it fast? What do programs mean? What happens when they fail? The rest of the talk is going to answer all those questions. Let's start with where the operations come from. The design is grounded in principles from cognitive science, visualization, and diagramming. A lot of this work, if you're interested, across different fields and decades, keeps leaning on the same small set of ideas, and these ideas are basically where the operations come from. Which raises the question, is a vocabulary this small expressive enough for the diagrams programmers actually need? There's no benchmark for us to compare against here. I don't know how you'd want your value diagrammed in general, but there's a class of values for which we do have conventions. Data structures. We draw trees growing downwards, our stacks growing up, matrices as grids. So where can we find lots of data structures drawn the conventional way by somebody who's not me? You all familiar with this book? It's influential. It's an algorithms textbook known for its high coverage and carefully professionally drawn diagrams. If you learned algorithms through this book, you probably have some idea of how diagrams should be drawn, informed by this book. There are 22 core data structures in the book with corresponding diagrams. Spatial was able to recreate the essence of all 22 diagrams from corresponding Python implementations with very few refinements needed. The most was interval trees at 11 operations. So you can really just get these diagrams really quickly with often just five lines of code from the default. Okay, so it's expressive, but you also don't want to wait around forever to see a diagram. The REPL produces an output immediately, and that's why people like it. So does it run fast? Yes, graph goes up. Diagrams for most CLRS data structures render in under a second, well past the sizes of REPL output you normally inspect. Even at the high end, render times are roughly within standard interaction bounds. And I think the worst we got was 10 seconds for a really gnarly B tree. But all of this has been I've been talking about using the language. We're a PLDI. What does a program really mean? A spatial program is a set of constraints. And its denotation is the arrangements of the value graph that satisfy all of these constraints. The interaction video I showed you earlier is actually this denotation at work. You can drag elements around as long as the resulting arrangement is within the denotation. The empty program denotes every arrangement, which is how you get this diagram for free at the beginning. And then if you don't write any constraints, you just get the default graph. You got the empty program. And most importantly, and this is the crux of the paper, adding a constraint strictly refines the space of allowable arrangements. You can rearrange things, carve things out, but you can never invent stuff that isn't in the underlying value. The diagram you see is always faithful. And if the denotation of your program is empty, you know that it's unsatisfiable. It allows no arrangements, which raises the question, what happens when rules conflict? Let's add some constraints to our existing BDD diagram that say low edges go to the left and high edges go to the right. It may not be obvious looking at it right away, but it's not satisfiable for this BDD. So what's Spatial going to do? Like any well-principled tool, the first thing Spatial does is construct an error report roughly analogous to an unsat core. Basically a small set of diagramming rules that cannot be satisfied, and you can get that sort of error report in terms of the diagram elements or the general rules you wrote. But here's the problem with a purely textual report. The whole reason I want Spatial is because diagrams help me understand structure. The very moment I need a diagram most, a textual unsat core doesn't really help me out at all. So Spatial makes the error report diagrammatic. It draws a counterfactual diagram, what the value would look like if just the offending constraints were relaxed, and highlights the offending elements and links them back to what caused the conflict. Basically, the diagnostic itself is a diagram. And in our studies, these counterfactual diagrams, unsurprisingly, led to much faster comprehension than textual unsat cores alone. Hopefully, I've kind of persuaded you that Spatial is worth trying out. Maybe you want diagrams. when you inspect values, and we should have this kind of inspection everywhere. So then I hear some of you thinking, does it work for my language? To study this, we integrated Spatial into 3 languages that occupy very, very different spaces on the programming languages spectrum. We have Python, which is super dynamic, runtime introspection, mutation, Rust, which everybody here loves, I think, statically typed, safety, and then Pirate, which is an educational language designed for teaching data structures with explicit ADTs. And, what we found is that if you hook into the same mechanisms the language uses to expose structure, basically what the REPL or the debugger would use, each language lends itself to the same rules and the same semantics. Which means if you want Spatial in your favorite language, the only thing you really have to do is hook into that mechanism. The diagrams, operations, error reports, interactivity, you get all of those for free. I mean, here's Spatial running in a Jupyter notebook, inline, totally for free. Basically, Spatial gives you a diagram when you need to inspect a program value. You start from a free graph representation of the value, refine it one constraint at a time, and stop when it meets your needs. You can play with our CLRS data structures here, learn about or install it in Python or Rust here. And I'm on the job market this year, so this is a really good time to argue with me about diagrams. Thanks so much. Yes.
Thank you. We have 5 minutes for Q&A.
Thanks. This is very cool. So binary decision diagrams are often implemented with, instead of pointers for low and high, integer IDs into like a node table.
Yes.
Does Spatial have some way of handling that kind of indirection?
Absolutely. You can, let me go to a slide of the, yeah. So one thing you can do in Spatial is while you can't invent nodes, you can invent what I call inferred edges. These are kind of like, when you're doing a program, when you're doing a proof, sometimes you have these like ghost fields you input. You can basically say, draw an edge that matches this relational selector. And so you can do that to kind of simulate edges from an implementation. It's like kind of similar when your backend is an array, but you want to see a heap kind of thing. Yeah.
Hey, so this is Rachit from MIT. Great talk, beautiful work. I wanted to go back to the question about larger diagrams.
Mm-hmm.
One thing that I really want to do if I'm looking at BDDs is generate really big ones and be surprised about why ordering of certain variables is causing issues in my particular domain, right? And so in that case, we really do care about really big diagrams where we don't know which section we want to focus on, and we're looking for surprise. I'm curious what mechanism and sort of how you think about this problem and how you can help me solve it.
Yeah, so I think about this in 2 ways. Number one, generally I think of like, when I look at anything in a deep, like in the REPL, beyond 50 nodes, I'm like, all right, I'm not able to like it's already like scroll down to the next page, right? So in general, that's why I kind of thought about this up to 50. That said, like, there's nothing preventing Spatial from rendering things that are larger. It just might take a little longer. It's also just the first layout. Once the solver is solved, you're good. Yeah, for that.
Thanks.
Yeah.
Hi, this is Justin from UC Berkeley. Thank you so much for the lovely talk. Really enjoyed it. I really appreciate that you think about what happens when the constraints are unsatisfiable, and I liked your analogy to the unsat core. But something that struck me as interesting is that you have this sort of like linear process of creating the program, of like you're refining the graph one by one, whereas in something like sat, all the constraints are kind of there, and then you like run it, and you don't know like what to do. So I'm wondering if you can like exploit the way that like people are actually like writing these refinements to get maybe even better sort of error handling.
Yeah. So in one sense, Spatial is fully order independent because of this sort of set-based semantics of constraints. So you could give it everything just like you give a sat solver, and it would produce exactly the same behavior. I think the really neat idea is that what I think people can exploit is you write all your rules and now you can toggle them on and off, and because of these refinement semantics, it never behaves weirdly, so you can kind of really isolate where it came from. Does that?
Yeah, Thanks for the talk. Seems like a very cool tool. One thing that I sometimes want to do is to be able to view the state of some system across multiple time steps, so across multiple diagrams. And ideally, I don't want the nodes to be jiggling around from one diagram to the next. Is that something that you support or that you could add?
This is a great question. So something I'm looking into right now, spatial, each diagram is independently laid out. So this is like some union find algorithm, and basically when you add some parent to satisfy the rule, spatial does a full reload and everything there goes there, basically. I have some thoughts about using soft constraints to kind of keep things in place. And newer versions of the system have some mechanisms for this. But yeah, so I'd love to chat with you more about that. Yeah, awesome.
Thank you for your talk. One thing I did not get is, do you only take the REPL output and construct it, or can you monitor a runtime data structure?
Oh yeah, so the REPL is just an analogy I'm using. It's any way you would like any way your language exposes structure. Like Rust doesn't have a REPL, but it has a serializer, and people use that to kind of keep track of what's going on. It's all of these different languages have different ways of exposing structure. So as long as you can tap into that, and most languages provide hooks.
Do you think this can be extended to simulate algorithms on the structures?
So I think that's the same, a little bit of the same question, right? Like with algorithm visualization, you can naively. I think the main thing is what's very useful is often having these sort of softer constraints of keeping nodes in the same general area if you can help it to prevent this kind of jitter. Yeah.
Okay, thanks.
But yes, long story short.
Hi. I think this is a very timely needed software. My question is, I work with a lot of sparse tensors. How would you represent them in this in a graphical structure?
Yeah. It depends on how the language represents them. So often
like Python sparse tensors, PyTorch, for example.
So I couldn't tell you specifically about sparse tensors in Python, but maybe this is an example of, it's really nice that spatial doesn't add values to the graph, but you get the actual underlying structure that the language exposes.
So my next question is that this example would work if the tensor is small.
Yes.
But the tensors that are usually used in practice are huge. And so I was wondering the scalability with the number of nodes.
Well, I guess my question is, would you ever print out the huge tensor?
Yeah, for example, if I want to see is there a structure in this sparsity, so I would print it out, for example, one row per line. So I would use the whole screen, but I'm not sure how would you represent in a graphical way like this.
So spatial can run across all of these different sizes. The question is, you need to be able to write the rules, then to refine it to the structure that works for you. But I think the general analogy is anything that's at the size of the REPL is kind of the size you can, or debugger is the size you look at things.
Okay, let's thank our speaker again. Now we will move on to our last speaker. And our last speaker is Yi He, and he will be talking to us about his work on persistent iterators with value semantics.
Okay, thanks for the introduction. My name is He Li from National University of Singapore, and today I would like to present joint work done by me and Gregory on persistent iterators with value semantics. The main idea of our work is to bridge two seemingly incompatible program paradigms, persistent data structures and iterator-based programming. To set the stage, let's first establish what we mean exactly by persistence. To simply put, persistence just means that objects are never mutated after their creation. For example, take the classical example of creating a widget. When we create it on some coordinates and then draw it, afterwards we create a reference to it and then modify it in place. This is not persistence because modification done on W is in place, and it will also modify V, of course. And that's a remote in-place modification that is the source of many aliasing hazards. Instead of this, let's imagine a persistent world where we are not allowed to mutate an object after its creation. In this world, we see that we can only rebind the widget to another value instead of modifying in place, and rebinding it will not affect V at all. There are some other advantages of persistence, such as avoiding spooky remote in-place modification, as I shown above. There are no side effects possible when we call a function, and also it allows for better optimization because there are no aliasing possible. Due to these advantages, in 2026, there is actually a trend to introduce persistence in many popular languages, libraries, and systems, such as Immer, functional programming languages, and Verse. So why is that? As I shown before, there are many advantages such as safety, predictability, and arguably better ergonomics. Of course, there's also some disadvantages of introducing persistence, that is different abstraction. In classical persistence languages, they use a fundamentally different abstraction. For example, in functional programming languages, we are more familiar with combinators and recursion instead of loops and iterators that are more familiar to traditional languages programmers. This is good in its own, but we must admit that objectively, these abstractions appear rare due to the relatively low adoption of functional programming languages, and this constitutes a great obstacle of adopting persistence in many traditional programmers simply because they are not familiar with this kind of abstractions. And this is exactly what our work set out to do. We want persistence without changing the abstraction to bring familiarity to ordinary programmers. Our work, persistence iterator with value semantics, basically want to bring persistence while retaining the familiar abstractions. To further illustrate how that works, let's look at a concrete example. Suppose we want to filter the unwanted elements from a bag of elements. For example, we want to remove all the colors from this bag of colors that are surrounded by brackets like this. So how can we implement this with imperative programming languages, and how can we implement this with functional programming languages? It turns out that the solution in both paradigms are very different and inspiring. Let's first look at an imperative programming solution. This is an example solution in C++ that uses step-by-step reasoning with familiar constructs such as loops, variables, and iterators. In this solution, we can see the familiar iterator abstraction used to iterate through the collection. We can also see explicit state management done by the variable want. We can also see how exactly this solution works. So in one iteration, if we want to retain the color, the iterator will just move to the next element. However, if we want to remove the color from the collection, we call erase on the collection, and that will return actually the next element after the remove element, and this will also move iterator to the next element. In this case, we no longer need to increment the iterator itself to avoid skipping over some other elements in the collection. However, the solution is not really persistence, because iterators in C++ are generally references of positions instead of standalone values. And also this is directly modifying the data structure. We are calling erase on it in place, and we are violating the no modification of the creation rule. So in conclusion, iterators in traditional languages are seemingly not persistent, as they are mutable references inside of containers. This also brings with it some safety hazards directly due to the lack of persistency. For example, this is firstly a slightly awkward API design. We must rely on the erase method returning the next iterator position. And this is also easy to get wrong and suffer from iterator invalidation hazards. For example, an easy mistake made by many beginner or even advanced programmers is to just not capture the return value of the erase method and instead just leave it here. In this case, we see on the bottom that the iterator will be still pointing to the remove element. And in the next iteration, when we try to dereference it, it will be a use after free hazards. Similar hazards like this are the direct reasoning why we want to introduce persistency in traditional languages. Now let's look at how functional programming solves the same problem. FP languages like Haskell avoid such problems because all data structures are assumed to be persistent in there. So in this example solution shown here, we can see that there are no modification, only composition here, and persistence is enforced everywhere. This is obviously good. However, the Haskell solution also has its own problems, so it relies on combinators, specifically two-pass combinator, because there are no built-in support for step-by-step modification. We must rely on reverse. This is a completely different abstraction compared to the previous solution, which incurs loop and iterators, and this is unfamiliar to many programmers. So this is where our work comes in. We want to answer the core question: is persistence and iterator fundamentally incompatible? Well, if we look at this solution, we can see that seemingly yes, because we are trying to modify the container in place, and iterator references position, not value. However, this can be changed if we give iterator value semantics. In fact, by giving iterator value semantics, we can imagine in that world, each iterator will now hold its own snapshot of the container. So when we call erase on the iterator, it will be pointing to a new snapshot of a new container that doesn't contain this element. And the original container will be intact because we are only modifying a snapshot. By following this reasoning, we can see that persistence is actually only incompatible with reference semantics, not the iterator abstraction itself. Now, this is how the STL iterator works, and this is how the new code in our library works. So we can see that to achieve persistent iterators, we only need to change reference semantics to value semantics and introduce a few syntax modification. For example, while we are still using iterator to iterate through the container, we now call erase directly on the iterator because we want to modify the snapshot, not the container itself. Also, we need to materialize the snapshot back into its own container at the end, because after the loop, the original container will still not be modified, and if we don't materialize it, the whole loop will will have no effect after all. You may wonder if this is inefficient. After all, in each iteration, we are creating new snapshot of the middle states and with partial element removal, and that may be inefficient in a traditional sense because you may imagine it is copying all the elements. But by carefully designing the data structure, we can show that this is not actually inefficient. In fact, we implement our common containers in our library with a single unifying underlying data structure called finger tree. It's basically a complexly modified version of the binary search tree that allows amortized O1 access to ends, which is ideal for things like vectors and other sequence containers because they generally rely on very efficient access to both ends. Also, this is obviously very suitable for sets too, because sets are just implemented as trees in most languages too. Furthermore, iterators are now realized as zippers on the trees, which just means that it keeps track of all the nodes from itself to the root and all the intermediate nodes. When we try to add or remove elements through an iterator as shown on the bottom left, we can see that we only need to recreate the subtree that contains a modified segment and can reuse most of the intermediate nodes up until the root. This makes copying very efficient. In fact, it makes copying entropy in amortized constant, which solves the efficiency problem. In fact, by carefully went through all the algorithm complexity and comparing them to the standard library ones, we can see that in the majority of cases, container operations actually have the same or better complexity when compared to their STL counterparts. In the image shown on the left, the yellow blocks show the case where the time complexity is the same, and the green parts show where the complexity of our library is actually better. Of course, there's no free lunch, and there exists some unavoidable trade-off in some operations just due to the limitation of tree structure. But in general, we think that at most it's a logarithmic time slowdown, and that is very worth it when we treat them for the various advantages of introducing persistence. We also done some micro benchmark results on our newly introduced persistent containers and compare them to both the standard library and several third-party popular libraries in C++, such as Upsil and Foley. We can see that persistent containers does have a large constant factor than popular libraries. For example, in vectors, it's hard to beat just a sequence read, just due to indirections and tree transversal costs. However, in some cases, we can see that our library actually has an algorithmic efficiency, and in most cases incurring sets operations, we can see that our library performs comparatively well compared to other third-party libraries and the STL. We also done some benchmark results on using iterator operations instead. We can see that the persistent iterators are low constant time update erasure, but with similar constant factor overhead as using the containers themselves. We can see that this graph is very similar to the ones in the previous slide, showing that they basically have the same performance characteristics. Finally, we also benchmark the memory usage of our library compared to common third-party libraries. Our implementation use reference counting, so all the intermediate states that are no longer referenced will automatically be collected. As such, our containers or iterators exhibit comparable memory usage patterns compared to most popular libraries. So you can see that the green line showing our library is very similar in characteristics to other libraries. So in conclusion, our library has shown that persistence is in fact compatible with many familiar idioms in traditional languages such as loops and iterators, as long as we just get rid of reference semantics and embrace value semantics. Our library tries to be safety by design and introduce a better ergonomics by introducing persistence without changing the familiar APIs. And we also show that our library have comparable performance and competitive complexity compared to major libraries across all the third-party or the standard library. So you can scan the QR code for more information on our library, and thank you for listening. That's all.
Thank you for the talk. We have 5 minutes for Q&A.
Thank you. Very interesting work. I was just wondering how hard it is to get from the current code, the current iterator code, to your new iterator model. Did you inspect that?
Okay, yeah, so that is a very good question. And it's actually, even though it's pretty familiar API, it's still a paradigm shift. So so when we move from traditional iterator to our code, it's not a trivial task. But we have used our iterator library internally in many large projects, and we would say that using it to develop has roughly the same complexity as using the standard library. So I ultimately don't think that change to this, our library will incur a very high mental cost or anything like that.
Hi, thanks for the great talk. I have two sort of related questions about like sort of, I guess, different directions for benchmarking this. The first is, have you tried, any small finger tree optimization sort of things to offset the large constant factors for the implementation? And second of all, obviously this is not an efficient idea, but I'm curious, like, if you were to implement reference semantics naively with like traditional looking data structures, how bad of a slowdown do you get? Like how much are you improving upon by bringing value semantics to like a more naive implementation that uses,
Yeah, that is two actually very good points. We have actually think about using small finger tree optimization, but ultimately we didn't really pursue that case as there's a bit of implementation difficulty. But we definitely try to bring it to fruition in future work. Also, we try to optimize the performance of allocating so much small objects by changing to a slab allocator anyway. So we don't think that using that optimization will change the performance characteristics very much. As for using traditional libraries with reference semantics, I believe that if we try that, we need some like major solution that is accepted by industry to make our comparison more like convincing and things like that. So we haven't actually done that yet, but thank you. We will definitely consider this in a future comparison.
Thank you very much.
Does this work with iterator insertion as well?
Yeah, it does. In fact, in the finger tree diagram, we have actually shown how insertion works, not erasure, but they work similarly.
It's pretty cool. Thank you.
Any more questions from the audience?
Very interesting work. Thank you for a very good talk. I was just curious, and this is going back to the first question. Conor McBride had this idea of these zipper-like structures can be obtained by differentiation. So could you take traditional implementations and just apply a derivative-like operation on all of them in order to get your persistent iterator structures?
Yeah, maybe I believe it will be possible, but either way, it will require extensive modification of those traditional libraries too. So I think it will be better if
you could probably make a parallel set of equivalent libraries.
Yeah, it makes sense, and we will consider it and maybe compare to such an implementation in the future, I believe.
Thank you.
Let me have one final quick question. So would you please summarize the characteristics of the usage cases where people should choose your persistent iterator over the mutable iterators? Or how would the developers make the most informed decision on which type of iterator to use in their own programs?
Okay, that is a pretty good question. I believe that the main choosing criteria probably would be based on how much you value the advantage of persistence, such as how much you want to avoid aliasing or how troubled are you in real work with those kind of remote modification and things like that. So if you are really advanced C++ or other language programmer and you don't really care about those and you can write correct programs, I believe you don't need to switch to this anyway. And maybe it's more tailored towards like a middle field or beginner towards project for something like this.
Okay, thank you. Yeah, let's thank our speaker again. With that, this will conclude this session, and thank you for attending, and I hope you will
Okay. Good afternoon, everyone. I hope you enjoyed lunch. Welcome to the probabilistic programming session. I'm Faraz Saad. I'm an assistant professor at Carnegie Mellon University, and I'm hosting the session today. So we will have a nice lineup of speakers. We'd ask to keep the questions mainly for the end, except for any quick clarification questions. Okay. So our first speaker is Haley from Aarhus University. They are presenting their work on Foxtrot, which is a separation logic for verifying properties of probabilistic concurrent programs. Take it away.
Testing, testing. Well, first of all, congratulations, you're halfway through PLDI. So we'll celebrate this by starting off with a puzzle. And this puzzle, I will give you an example program, which I call two threads. At the very beginning, we use the parallel composition operator. So we have two threads running at the same time. And each thread samples a random number. It samples a number using the primitive rand. And rand n, in our operational semantics, samples a number uniformly from 0 to n with probability 1 over n plus 1 each. So in other words, rand 1 is just a fair coin toss that returns either 0 or 1 with 1/2 probability each. That gives us two numbers, x and y, and we return x times 2 plus y. And my question for everyone here is, what exactly is the behavior when you call this function? To analyze this, what you can do is that you can enumerate all the possible values of what x and y is. And that gives you a table or so. And you can see that the final value, x times 2 plus y, actually is just all the numbers from 0 to 3. In other words, calling this program returns a number from 0 to 3 uniformly with 1/4 probability each. Another way of saying this is that the behavior of this program is actually the same as the simpler one that directly samples with rand 3 as a primitive. So now, if we want to show if these two programs behave the same, can we actually prove that they actually behave the same? To actually prove this, we have to actually define what it means by two programs behaving the same. And a good notion of that is contextual equivalence. Contextual equivalence, if we want to say that E1 is contextually equivalent to E2, what that means is that if you consider all possible well-typed contexts, which you can consider as like larger programs with a whole, and depending on whether you substitute E1 into the whole or E2, it doesn't matter. The observable behavior of CE1 or CE2 is exactly the same. In general, proving contextual equivalence is defined as the symmetric closure of contextual refinement, which is basically the same, except instead of equality, you have the subset relation. Now, proving contextual equivalence or refinement is pretty hard. One of the reasons is that we're quantifying over all possible contexts. In our case, for proving two threads, it's even more difficult because we have both randomization and concurrency in the implementation of two threads. Now, both of these features are useful. For example, you can use it to implement concurrent randomized algorithms or data structures, like the concurrent approximates Morse counter, or you can use it to model cryptographic protocols, like secure multi-party computation. But these two language features in combination is very hard to reason about. And formal methods for these programs are quite limited and not very expressive. In particular, to the best of our knowledge, there were no techniques that you can actually use to prove contextual refinement of concurrent probabilistic programs. To solve this issue, we introduce Foxtrot. So what on earth is the Foxtrot? Foxtrot is the first higher order separation logic for proving contextual refinement of concurrent probabilistic programs. It is a very expressive logic, and you can use it to reason about higher order programs or those that utilize higher order local state. We formalize Foxtrot in the ROC proof assistant on top of the iris separation logic framework. And despite its name, it has nothing to do with foxes, nothing to do with trots. The key weapon that Foxtrot utilizes to prove contextual refinement is a refinement judgment proposition that lives inside the logic, written as so. Intuitively, if you're able to prove this proposition, it means that E1 refines E2 at the type tau inside the logic. And we have a soundness theorem that says that if you're able to prove this refinement judgment inside the logic using inference rules, this implies that E1 contextually refines E2 at the meta logic. To construct this refinement judgment proposition, we started off with the iris-based logic, on top of which we built the Foxtrot model implemented using expressed as weakest preconditions. We then construct a binary logical relation using the model, and we use the logical relation finally to define the refinement judgment proposition. Now, this chain to derive the refinement judgment is not novel. It is quite standard, and it's used in previous logics like reloc, clutch, or proxies. But what I emphasize is novel is how we define the model of Foxtrot. And because we have both concurrency and probability in our language, this model is different from previous logic, which I'll explain a bit later. Because Foxtrot is built on top of the iris-based logic, we immediately inherit all the nice reasoning principles for reasoning about concurrency. For example, we have impredicative invariance and ghost resources. Foxtrot is also inspired by various logics for reasoning about probabilistic programs, and it supports a wide range of logical facilities for reasoning about probabilistic principles. For example, we have error credits from Eris and fragmented coupling from Aproxis. It should be emphasized that getting all this to work is not straightforward. This is because the model of Foxtrot is different from previous logics, and we have to prove a lot of these principles from scratch. In particular, some rules, for example, a whole class of rules which we call presampling on the right, is unsound in our logic, which we have a counterexample in our paper. Let us take a step back and have a revisit the example I presented at the beginning. Let's prove one direction of the refinement, and I also generalized the sampling from ran1 to some arbitrary n and m for both threads. The key idea of this proof is that we have to be able to relate the ran sampling on the left and the two random samplings that happen concurrently on the right program. To do so, Foxtrot introduces this rule that allows you to relate one ran on one side and two rans on the other. And you can see that in the goal of this rule, it exactly matches what we want. And under a coupling reasoning principle, it suffices to prove that if the two threads on the right samples some arbitrary n and m, you can assume that the left-hand side samples exactly small n times big M plus 1 plus small m. And if you continue to symbolically execute, especially the right-hand side program, you can show that these programs eventually returns the same number, and that concludes the refinement proof. Now, this is one direction of the refinement, and to prove the other direction, you use a similar reasoning principle, but in particular, you have to use presampling tapes, which was first introduced in the clutch logic. As another example, we considered a implementation of a sampling function in the lib-sodium library. Libsodium is a widely used and well-respected cryptographic library, and it has this function, and as you can see from the implementation, it is quite straightforward to see what it does. Okay, I lied. It's not that straightforward, and that's why it's useful to show contextual equivalence. And as you can see from the simpler program, this just does some simple bounds check, and if it passes, it returns a random number from 0 to n-1 uniformly. Now this equivalence is harder to prove for various reasons. One of them, as you can see, is that the sampling on both sides are sampling from different domains. Another thing that's quite tricky is that on the left, you actually have recursion, but you don't have recursion on the right. And finally, our result is stronger than those in previous logics because our equivalence also holds in contexts that might utilize concurrency. And this gives us more guarantee that the implementation is thread safe. To prove this equivalence, you have to utilize fragmented couplings and error induction, both of which are logical facilities introduced in previous logics. Now that I've given you sampled a taste of what are the examples we can prove, I want to take a step back and talk a little bit about the details of the model of Foxtrot. And recall that the soundness theorem of Foxtrot says that if you can prove this refinement judgment in the logic, that will tell you that will imply contextual refinement in the meta logic. To even state this theorem, we have to be a bit more precise about the operational semantics of a concurrent probabilistic program. And because we have both probability and non-determinism induced by concurrency, our operational semantics are parametrized by scheduler. This scheduler is a device that helps us resolve all the non-determinism of the execution of a program. In particular, it decides which thread to step next. More precisely, the scheduler is a function that takes in its internal scheduler state and the current configuration and returns a distribution of the next scheduler state it updates to and a natural number representing the next thread to step next. Now, because our operational semantics now has to take into account schedulers, so does the model of Foxtrot, and we bake in the definition of schedulers internally into the model. Let me give you an intuition of how that works. And to do so, we will have to go back and consider logics for proving contextual refinement for concurrent languages. So we ignore probability for now and just consider contextual refinement for concurrent language. For example, the ReLOC logic. If we look at the adequacy proof of ReLOC, it says that if you're able to prove this Hoare triple, what this means is that if you unfold this weakest precondition, then for every single step execution for E1, you can find and construct a witness trace for the right-hand side program such that their endpoints are related. And then, by taking induction on the number of steps for the left-hand side program, you will get a number of traces on the right for E2, which you can then combine to produce one master trace. Then you can conclude that for every execution trace for E1, you can find an execution trace for the right that witnesses this refinement. Okay, so this is the case for concurrency. What if we just consider languages with just probability and no concurrency? Well, it's slightly different because now instead of a single line representing the trace, we now have probabilistic execution trees to take into account probabilistic sampling. And we consider that for every single probabilistic execution tree for E1, the the adequacy theorem says that you can actually find a possibly larger tree for E2 such that their endpoints are related. In particular, there's coupling between the leaves. And then at the end, when you take induction on the number of steps for the left-hand side program, you will get a number of execution trees on the right, which you can then piece together to show that for every tree on the left, it will refine some tree for the right. Now, finally, in Foxtrot, when we have both concurrency and probability, now we have to take into account schedulers. And we quantify over all possible schedulers, and we consider every single step probabilistic execution tree of that scheduler zeta. And the logic will show that you can construct a scheduler for the right-hand side such that the probabilistic execution tree induced by the scheduler witnesses this coupling. At the end, we will take induction on the number of steps for the scheduler on the left, which will give you a number of schedulers for the right, which you can then piece together to construct one master scheduler, to show that for every scheduler on the left, there is another scheduler on the right, such that it witnesses a refinement. And this concludes the proof. What is interesting is that to piece together these schedulers, we actually have to use the axiom of choice, which is both interesting and gross at the same time, depending who you ask. In conclusion, we introduced Foxtrot, which you can use to prove contextual refinement of concurrent probabilistic programs. And it is very expressive in the sense that it can be used to reason about programs that utilizes other challenging language features like higher order functions or local state. There are more interesting things in the paper that I encourage you to check out. For example, the detail of how the model is constructed and its proofs. And also we have quite a lot of other interesting examples to show that our logic actually scales to other interesting case studies. Finally, I want to end by saying that my advisor is currently recruiting interns and PhD students. So if this is the kind of topic that really excites you, feel free to catch me later after this talk. Thank you all.
Okay, thank you for the very nice talk. We have some time for questions. So please raise your hand.
Thanks, Ali. Great talk. I was wondering, your schedulers, are they allowed to depend on the computation history when they make their decisions?
Yes. So recall that the definition of the scheduler takes in a scheduler state and a configuration. So the scheduler state can be defined to actually record the whole execution trace.
Do you know whether it actually makes a difference if you say they're only allowed to depend on the, say, current state and not on the history?
That is quite difficult. That's an open research problem because you're now considering a smaller class of schedulers, and that is something we're looking into, where we're looking to see whether we can prove refinement of smaller classes or more interesting classes of schedulers. At the moment, our schedulers is quite general, so we're talking about all possible kind of schedulers, including those that record everything.
Cool. Great work. Thanks.
Thank you.
Thank you for the great talk. And we are also working on concurrent probabilistic protocols. So do you think your language can now express something like consensus protocols? Because that would be the case. That would greatly simplify our work.
That is a question that I can't answer right now, but I'm happy to, we can discuss later.
Yeah, sure.
We
are working on something more complex.
I'll be interested to see, whether there's any particular features that you use that we cannot support.
Okay.
Thank you.
Yeah, we have time for another question.
Thanks for the fantastic talk. What about divergence?
So, as in the program does not terminate?
Yeah.
So we have the same reasoning principles as in previous logics. For example, in ReLoc, if the left-hand side program does not terminate, then there's a refinement trivially. So that we inherit that same reasoning for our case. For example, we have loop induction that you can reason about programs that might never terminate. Thank you.
Okay, great. Let's thank our speaker one last time. The next speaker, come up, please. All right, our next speaker is Satoshi Kura. They are talking to us about verifying properties of probabilistic programs, and in particular, computing bounds.
Okay, can you hear me? All right, thank you for the introduction. Okay, can you hear me? Right, sorry. So this talk is about the quantitative verification of probabilistic programs. So many properties of probabilistic programs are quantitative in nature, and for example, the termination probability is real number between 0 and 1, and also the expected runtime is a non-negative real number or infinite. So there are many such quantitative properties. And our goal is to verify lower bounds of such quantitative properties. And it is known that many of these quantitative properties can be characterized as least fixed points. So here, K is a monotone function that is induced by a predicate transformer. And in this talk, I will often represent the least fixed point as the least solution of a fixed point equation. Okay, so here's an example. So consider a biased random walk, which is biased toward the origin. And in this case, the expected runtime is given as the least solution of this equation. And here you can see that the right-hand side of this equation has a similar structure as the loop body of this program. And in general, we can easily define a translation, inductively define a translation from a given program to such a fixed point equation. And verifying upper bound is relatively straightforward, and this is because by the Nassau-Tarski theorem, to give an upper bound of the least fixed point, it suffices to find a prefixed point of K. One advantage of this approach is its generality, and so this theorem applies uniformly to any property that can be characterized as a least fixed point. On the other hand, verifying a lower bound is much more challenging, and so one naive approach to verify lower bound is to apply a clean iteration like this, but this may require a large number of iteration, and in general, there's little hope of obtaining the exact value within finitely many steps. And yeah, several alternative approaches have been proposed, but yeah, they are typically tailored to specific properties, and yeah, do not apply uniformly because yeah, they do not directly exploit the least fixed point characterization. So in this work, yeah, we address this issue, and we propose a new reasoning principle for reasoning about lower bounds of least fixed point. So our main theorem is shown here, but you don't have to understand it now. So I will explain this in the next several slides. But based on this theorem, we also implemented an automated verification tool that automatically applies this main theorem to concrete problems. Okay, so now let me explain the main ideas behind our theorem. So the first key observation is that verifying lower bound become much easier if fixed points are unique. So recall that by the dual of the Naster-Tarski theorem, any post-fixed point gives a lower bound of the greatest fixed point. So if the least and greatest fixed point coincide, then any post-fixed point also gives a lower bound of the least fixed point. So then the question is, how can we guarantee the uniqueness of fixed points? So let's first consider the special case where k is bounded by 1. In this case, it is known that almost sure termination guarantees the uniqueness of fixed point. Intuitively, the gap between the greatest and least fixed point corresponds to the contribution of non-terminating execution passes. So, yeah, if the program is almost surely terminating, then this gap vanishes and the two fixed points coincide. And moreover, almost sure termination can be witnessed by ranking supermartingales. So, yeah, therefore, the existence of a ranking supermartingale guarantees the uniqueness of a fixed point. And it is straightforward to extend this result to the case where k is bounded by a constant m. However, this generalization is not enough because, for example, in the random walk example that I showed earlier, the expected runtime cannot be bounded by any constant. So yeah, this generalization cannot capture such cases. So to handle such cases, we consider a more general setting where k is bounded by a function u. In this case, restricting the domain of k is always possible, but on the other hand, restricting the codomain of k is only possible when u satisfies this condition. So so we assume that u is a prefixed point of k. So, but in this setting, almost sure termination is no longer sufficient for guaranteeing the uniqueness of fixed point. So we consider a generalization of a ranking supermartingale. So this is the key idea of this work. So to guarantee the uniqueness of fixed point, we introduced the notion of U-ranking supermartingale. So recall that a ranking supermartingale is a function R that decreases by at least 1 in expectation. So we generalize this definition to generalize this definition, we reformulate the definition by reformulating the ranking condition using the function k. And also, we replace the constant decrease of by 1 with the upper bound function u. So we define the resulting notion. So we call the resulting notion a U-ranking supermartingale. And we showed that the existence of a U-ranking supermartingale guarantees the uniqueness of a fixed point of k bounded by U. So then, once the uniqueness is established, then we can combine it with the Naster-Tarski theorem to obtain a lower bound. So this is the key idea of our main theorem, and the statement of our main theorem brings these ingredients together. So in our theorem we have four conditions, and the first condition ensures that k can be restricted by u, and the second condition states that R is a U-ranking supermartingale. And the third condition requires that L is a post-fixed point, and the last condition ensures that L is in the restricted domain of K. So under this condition, we can conclude that L is a lower bound of the least fixed point. Okay, so as an example, let's apply our main theorem to this random walk example. In this case, we can choose the functions u, r, and l as shown here. Then it is straightforward to check that the four conditions of our main theorem are satisfied by these functions. Then, by our main theorem, we can conclude that 3x is a lower bound of the least fixed point. And in fact, this is the exact lower bound of the expected runtime. I would like to emphasize that the assumptions of our main theorem is general enough. We assume that K is omega continuous, omega co-continuous, and affine. But typically, predicate transformers typically satisfy. Predicate transformers typically satisfy the condition of omega continuity and omega co-continuity, and moreover, predicate transformers for probabilistic programs usually satisfy the condition of affineness. And as a consequence, these assumptions are satisfied by all these quantitative properties are shown here. And also, we can obtain a stronger result by slightly extending our main theorem. So here, suppose that we have a function k prime that under-approximates k. Then, obviously, the least fixed point of k prime is also under-approximates the least fixed point of k. So, if we apply our main theorem to k prime, then the resulting lower bound is also a lower, the resulting lower bound is also a lower bound of the least fixed point of k. So this extension is quite simple, but it certainly increases the power of our main theorem. And specifically, it enables us to simulate several existing techniques for lower bound verification, including guard strengthening, stochastic invariance, and gamma scaling. Okay, so finally, I will explain our implementation and experiment. So we implemented an automated verifier, a mu-val QFL, that automatically applies our main theorem. So our tool solves a bound checking problem rather than a bound inference problem. So its input consists not only of a least fixed point equation, but also of candidate lower bound. The goal here is to determine whether the given candidate is indeed a valid lower bound for the least fixed point. So our tool, mu-val QFL, is based on template-based synthesis. So specifically, our tool uses piecewise polynomial template where the partitioning of the template is determined by the branching structure of the input equation. Then, our tool generates polynomial constraints and passes them to an off-the-shelf constraint solver called Polyquent. We evaluated our implementation on benchmarks taken from the literature and together with some additional benchmarks. And we use several configurations with different degrees of template, and some configuration enables the under-approximation technique using k prime. And this table shows the benchmarks checked against the exact values. And this table shows that our tool successfully solved all of these benchmarks. And here's another table which shows the result for benchmarks that are checked against approximate values. These benchmarks were more difficult and required an appropriate choice of configurations and more time. And improving this result may require improvements to underlying constraint solver and more sophisticated constraint generation techniques. And also, our current implementation has a limitation that it only supports polynomial templates. So extending this to other template is left for future work. Okay, so this is the summary. So we proposed a new reasoning principle for lower bound verification based on the idea of U-ranking supermartingale. And our implementation is available if you scan this QR code. So thank you for your attention.
Okay, thank you. We have time for a question or two.
Hi, thank you for a very nice talk, and this is really cool work. I have a question about the condition for the uniqueness of fixed point. So what you provide is a sufficient condition. Do you know if it's also necessary?
I don't think so. Yeah, it's just a sufficient condition.
Do you have a counterexample, or?
We currently don't have, but we don't think these are sufficient.
Okay. Very cool work. Thank you.
Thank you.
Anyone else? Yep. There's the microphone right behind you.
Yeah, thanks a lot. Honestly, this is something we've been waiting for quite some time. Very cool. Could you please go to slide 15? So I was wondering, do you think there is any hope to weaken that equality of K and the convex combinations you have there to an inequality?
You mean this one?
Yeah, exactly.
Well, sorry, I don't remember, but probably, if I remember correctly, we need exact equality and not inequality.
So. I think if you could weaken it, that might be cool, because I believe this equality breaks for programs that are both non-deterministic and probabilistic, like in Hailey's talk. And if it's only an inequality, your rule might be like generalizable also to these programs. Would be cool.
That's an interesting point.
Okay,
thank
you.
Great. So we already have the next paper that you're going to write based on this idea. Great. Okay, let's thank our speaker one last time. And our next speaker, please come up to the stage. All right, our next speaker is George from Singapore Management University. They are presenting their work on verifying algorithms for differential privacy.
Hello. Excellent. All right. Hi, everyone. Thanks for coming to my talk. So my name is George Zikilic, and this is joint work with Krishnendu Chatterjee and Sango Khashadi from IST Austria. So today I will talk about our method SuperDP for refuting differential privacy by using super martingales. So let's set up the stage for the problem. So we are considering differential privacy, which is essentially a formal notion for ensuring privacy of data, when basically extracting statistical data from, let's say, some database or set of information. So formally, given a privacy mechanism modeled as a probabilistic program, and given a notion of similarity of its inputs, we say that this mechanism is epsilon differentially private if for any pair of similar inputs, basically the total variance distance between the outputs, the output distributions of this program on these two inputs is bounded by e to the epsilon. So in other words, for any output event, the difference in the two probabilities differs by at most a factor e to the epsilon. And then we say that this mechanism is epsilon differentially private. Now the problem of checking epsilon differential privacy in general Turing complete probabilistic programs is undecidable. So of course we cannot have a single algorithm which can both verify and refute this problem. So people have focused both on DP verification on one hand and DP refutation on the other hand. And this is a very challenging and important problem because differential privacy is known to be, let's say, not very robust. So even minor tweaks to DP mechanisms can break DP guarantees. Now, recent years have seen a number of approaches and basically insignificant advances on this problem. And here I provide the summary. So I'm considering four, let's say, desirable properties. So one, of course, is full automation. Second is applicability to discrete and continuous distributions. The third is soundness. So basically guarantee that whenever a tool reports a DP bug, there is indeed a DP bug. And then finally, the fourth is semi-completeness. So what do I mean by this? So due to the undecidability of the problem, of course, we cannot have both sound and complete algorithm. but we could still ask for a sound algorithm which is guaranteed to catch a certain subclass of DP bugs. So some of the existing methods have focused on finite and discrete probabilistic programs. However, many differential private mechanisms use continuous distributions such as Laplacians or Gaussians. There is also a class of methods which use sampling and in some cases provide statistical guarantees. And these methods are automated and they support general distributions. However, they do not provide soundness guarantees. In some cases, they provide statistical guarantees, but as we observe in our experiments, sometimes it can also happen that they still provide false negatives, so report bugs in case when there are no bugs. CheckDP and its predecessors is a state-of-the-art static analysis tool, which is automated, provides soundness guarantees, is applicable to, well, they focus on Laplace distribution, but basically supports that continuous distribution. However, no existing method provides semi-completeness guarantees. And the question that we ask in this work is, can we have all four? So automation, applicability to general distributions, soundness, and also certain level of semi-completeness guarantees. And we propose this in our method called SuperDP. Now, the key idea behind our method is we take a slightly different view on differential privacy refutation. So a standard approach to detect the DP bugs is to search for a pair of similar inputs and an event on output such that we have this probability mismatch. Instead, what we search for is a pair of similar inputs and a non-negative function over the outputs for which we have expectation mismatch. So expectation of the function on the output on the first input is greater than e to the epsilon times the expectation on the output given the second input. Now, expectation mismatch strictly subsumes this because for any output event A, you can take its indicator function, and that's your function f. But now, what does guarantee that this is sound? So this might seem we are considering a strictly larger class of objects. Well, we still show that this is a necessary and sufficient condition for detecting DP bugs. So in other words, a program is not epsilon differentially private if and only if there exists a non-negative function over outputs for which we have expectation mismatch. So now we may perform a search over this larger set of objects in order to detect DP bugs. And why is this useful? Where for some classes of techniques, actually computing precise bounds on the probability of some events is quite challenging. Whereas there are also many tools for reasoning about bounds on the expectation of functions on outputs, which provide better quality bounds. And one such example of techniques is supermartingales, and in this work, at least to the best of my knowledge, we bring supermartingale certificates to the first time to the setting of reasoning about differential privacy. But before going into the details of our method, let me just give you an example of this expectation mismatch idea. So this is what is called the randomized response mechanism, which basically, if I have, let's say, some survey where participants provide yes or no answers, and now I want to query my database, I want to basically preserve the privacy of individuals. So what I do, if you query me about the response of a certain participant, with probability half, I will tell you their true response. And then with remaining probability, so 0.25 each, I will just tell you 0 or 1. So in other words, with probability 0.75, I'm telling you a true response of the user. And with probability 0.25, I'm telling you the opposite. So in that way, I'm trying to hide the response. Now, how can it is known that this mechanism is natural logarithm of 3 differentially private and is not differentially private for smaller values of epsilon. So how can we refute smaller values of epsilon? Well, we can use function over the outputs f, which is just equal to this output. So here I write output squared because this is what our tool computed, but because it's a Boolean 0, 1, this is just output. So the expected value of this function on input 1 is equal to 0.75. The expected value of this function on input 0 is equal to 0.25. So if I write my expectation mismatch inequality, I have 0.75 greater than e to epsilon times 0.25. And this holds exactly when epsilon is less than, so this is valid exactly when epsilon is less than natural logarithm of 3. So I can witness tight bounds using expectation mismatch. Now, of course, this doesn't solve the problem. I've just given you basically a new characterization of epsilon differential privacy. But the question is, how do I automate the search for this function? And of course, how do I automate basically reasoning about these expectation bounds? And for this, we are going to use supermartingale certificates, which have been already applied in probabilistic program verification and stochastic dynamical system verification to reason about various properties, including expectation bounds. So we're going to use something called upper and lower expectation supermartingales, which we used in previous works to also reason about equivalence of probabilistic programs. So these are proof rules for deriving upper and lower bounds on the expected value of a function and output, so which is exactly what we need to reason about expectation mismatch. So for upper bounds, what is an upper expectation supermartingale? So it's a function which to every system state assigns some real value, which is required to be equal to 0 upon termination. And then in non-terminal states, at every step, basically, the change in the expected value of this function over approximates the change in the value of f. So basically, if I consider how f evolves over a program, basically, I over approximate its change at every time step by using u. And this allows me to basically guarantee that, okay, this is a slightly simplified version. Basically, we have under conditions which are called optional stopping theorem conditions, which I'm not going to go into the details now, basically that U provides an upper bound on the expected value of f on output, and dually lower expectation submartingales for lower bounds. So we are going to use this as a tool to basically witness our expectation mismatch, because we cannot, in many cases, exactly compute the expected value of f on output, but we can bound it quite tightly by using these tools. So we propose a new supermartingale-based proof rule for refuting differential privacy. So we're going to search for 5 objects, 2 inputs, which are similar, non-negative function over the outputs, and then a pair of these upper and lower expectation supermartingales, which essentially allow us to witness this expectation mismatch. So the first, we have basically the first condition that we want these objects to satisfy. The 2 inputs should be similar. F should be non-negative function over the outputs. Now, L should provide me a lower bound on the expected value of f on the first input. U should provide me an upper bound on the expected value of f on the second input, such that this expectation mismatch condition holds. And this is essentially obtained by plugging in the guarantees of upper and lower expectation supermartingales on the expected value of f on output. And what we show is that, so this is sound, this follows from the soundness of upper and lower expectation supermartingales, but we also show that this is a complete proof rule. So for this particular application, we even get completeness guarantees. So this is a sound and complete proof rule for refuting epsilon differential privacy. And this is the important ingredient for soundness and semi-completeness guarantees. Now, okay, this still doesn't solve the problem of how do we compute them, but now we know what we need to compute. So if we want to refute epsilon differential privacy, we need to compute this tuple up there such that these 5 conditions are satisfied. And we use this by using template-based synthesis approach, which was also mentioned in the previous talk. So this is a general class of techniques for computing certificate functions. So basically you fix a symbolic template of a certain form. You collect the system of constraints over template variables which encode the conditions that you need to be satisfied, and then you solve. So in our case, we consider polynomial templates. So basically we assume that the program and the similarity relation can be specified in polynomial real arithmetic. And we basically fix symbolic templates, so for the 2 inputs, for the non-negative function outputs, which is going to be 1 polynomial expression, and for the 2 expectation supermartingales, so for each location in a program, 1 polynomial expression. And then we collect a system of constraints, which together encode these 5 properties. Now, I'm not going to go into the details, but essentially this gives you a system of quantified polynomial constraints over real variables. We have quantifier alternation, so that's not very nice to efficiently solve these. So we use a technique called Handelman's theorem, which allows us to, in this case, get rid of quantifier alternation, reducing the system to a purely existentially quantified system of polynomial constraints, which we can feed to an off-the-shelf SMT solver and solve more efficiently. And any solution to the system gives us a valid instance of this supermartingale witness for refuting epsilon dp. So we show that the algorithm is sound. It is also conditionally semi-complete. So what do I mean by conditional semi-completeness? So we showed here that this witness is sound and complete proof rule. But now we are restricting ourselves to polynomial real arithmetic. So our guarantees are, if this witness can be represented in polynomial real arithmetic, and if we use the needed polynomial degree, then our algorithm is guaranteed to find such a witness. So this is the semi-completeness guarantee that we provide. And then finally, the runtime of the algorithm is p-space, parameterized by the polynomial degree that you're using. We implemented a prototype, which we call SuperDP, hence the name of our paper. And we ask 3 questions. So first, how effective is our method compared to the existing methods in terms of examples that it can or cannot prove? How efficient it is in terms of runtime? And of course, what are the limitations of the method? So to answer these questions, we collect 15 benchmarks from the DP verification and refutation literature. Now, for not all of them do we know exact, privacy budgets epsilon that gives us type bounds. So we basically start from some low value of epsilon, and then we gradually increase it up to 15. And then for each tool, we report the lowest value of epsilon for which, its DP was refuted. We consider two baselines, CheckDP, which is a state-of-the-art static analysis tool for this problem, and then StatDP, which is a sampling-based dynamic method. And then for each benchmark, we set a timeout of 5 minutes. So this is the table of our results. I'll give you a summary of results as well. So basically, the green cells are, so in the first column, basically, the tightest refuted bound, the second runtime. So as we can see, Super DP performs decently. Now let me give you a more qualitative overview of results. So for 13 out of 15 benchmarks, we successfully refute epsilon DP with the lowest value of epsilon compared to all the tools. Now I will explain what happens with the last two examples when I talk about limitations. In most cases but one, in all cases but one, our runtime is less than 3 seconds, so we're quite efficient. For examples where epsilon less than 15 is sufficient, in 7 out of 9 examples we find lowest bounds. And then in 6, where epsilon needed is actually greater than 50, we refute 15. I don't know how I'm doing with time. Do I have... Okay, then I can go a bit into the insights, some more detailed insights. So this is, these are some examples of benchmarks where we observe different things. So for instance, this low prob benchmark is an example of where in order to refute the DP, you need to reason about low probability events. So this is typically a class of example where sampling-based methods will struggle because you need many, many samples to detect these. Super DP manages to refute epsilon differential privacy in this example. We are also able to handle examples with unbounded loops, which is also very challenging, such as geometric. And then we are able to handle a broad class of different probability distributions. So basically, the only thing that we require is that we have access to the first D moments, where the D is a polynomial degree that we're using in our algorithm. So this is good side. Now, what about the limitations? So I mentioned that we fail on 2 examples. And actually, the reason behind the failure is the same. So there is a construct which is common to these 2 examples. So basically, we have a sampling instruction from a Laplace distribution, and then we have conditional branching based on the result of the sampling. So in order to perform static analysis on this, you need to kind of symbolically reason about the probabilities of these bounds, which if you're using general probability distributions and then you condition based on the result, is challenging to capture accurately using polynomial arithmetic. So this is one limitation of our approach. So such constructs, we need to go beyond polynomial arithmetic. More generally, we are restricted to programs which can be represented in polynomial real arithmetic. So the similarity relationship between the inputs and all arithmetic expressions need to be polynomial. Now, this doesn't mean that our distributions need to have polynomial PDFs. They can have non-polynomial PDFs. So Laplacians and Gaussians are completely fine. We just need to have access to their first D moments. But the arithmetic expressions appearing in the program, they need to be polynomial. And then finally, we consider epsilon differential privacy, but there are also more general notions of differential privacy, such as epsilon delta. So this is a subject of ongoing work. We have some interesting results, and I hope that I'll be able to present them soon. So of course, addressing these 3 limitations is, naturally interesting directions for future work. And of course, another one is going to DP verification and trying to obtain sound and semi-complete algorithms there as well. Oh, wait. Oh, thank you, but I have one more slide. So to conclude, basically, maybe the key takeaway from our work is that we reformulate epsilon differential privacy as an expectation mismatch problem. So this is kind of a different view on epsilon differential privacy. And then one way to tackle it is to use super martingale certificates. So this is something that I've been working on for years, and I'm very happy that we're bringing them to a new application domain. So basically, one can design a sound and complete proof rule for refuting epsilon DP by using super martingale certificates for expectation bounds. Based on this proof rule, we design a sound, semi-complete, and fully automated algorithm for based on template-based synthesis for refuting epsilon DP. And our prototype implementation shows promising results. So we are able to solve 13 out of 15 benchmarks at good runtimes. And our tool is available, so you're welcome to play with it. And I haven't written it on my slide, but I'm also having openings for PhD students and interns. So if this sounds interesting, please come and talk to me. Thank you very much.
Thank you, Georgi. Any question from the audience? Yep, I'll give you the speaker. Yeah.
Hello, I'm Shaurya from UIUC. Very nice work. You mentioned to have used Handelman theorem while using. If my understanding of Handelman theorem is correct, it is only necessary if your space is bounded, like on a polytope. But if you are using continuous distributions, then the variables can be unbounded, right?
Mm-hmm.
So how does that work in that case?
Right, that's a great question. So soundness is not affected. So basically, this translation provides semi-completeness guarantees if the space is bounded. So you can use sampling from continuous distributions, but the support needs to be bounded.
Oh, so the semi-completeness comes from the fact?
Yes, needs to be. Well, you can have semi-completeness even without this. So this is done for efficiency.
Makes sense.
But if you want to have p-space runtime, then you need to apply this. Yeah.
Fair enough. Yeah. Thank you.
Other questions? Yes, in the back.
Thank you for the very nice talk. I was just curious, like, what degree of polynomials do you consider in your experimental results? Like
up to 5.
Okay, thanks.
All right, we have time for one more question. Yeah, Philip?
Thank you. Yeah, lovely talk. So you already mentioned that you're interested in extending this to epsilon delta. How about other notions of differential privacy? There's many more.
That will be interesting. We haven't considered, but yeah.
Okay.
So as the first next step, we started with epsilon delta.
Right. Yeah. Because those testing-based characterizations might start breaking down.
Yeah.
Interesting. Thanks.
All right. Let's thank our speaker again.
Thank you.
Our next speaker is Philip Hasselwarter, also presenting about differential privacy, in particular a program logic for verifying implementations of DP algorithms.
Yes? Is the mic on? Yeah? Cool. Okay. That's not my slides. Okay. Here we go. All right, thank you. Yeah, so there's going to be more differential privacy coming your way now. And we'll start with a little scenario. If you're not familiar with differential privacy, the whole goal of the exercise is that we want to protect sensitive data, right? We might have some kind of a medical data set where we have patient data, and we want to compute some statistics over this data set. So some function f that computes statistics, and we want to protect Frank's privacy in this data set. And so the way that differential privacy defines what that means is that we want to be able to release the statistics without even revealing whether Frank's data was in the data set in the first place. And so we do this by defining some kind of a hypothetical data set, d prime, where we remove the row that corresponds to Frank. And we call two such data sets adjacent. And then the question that we ask is whether f on d is somehow epsilon similar to f on d prime. And this epsilon here, we also call that the privacy budget, which, as we saw, gives us a sort of a bound on how much privacy we're leaking. And so if we just look at counting queries, so we can compute the histogram over the data set, and if we compare f on d to f on d prime, we immediately see that in the cardio category, the counts differ. So we can immediately recover Frank's data from this. So this is not very private. And what differential privacy tells us to do instead is that we use a mechanism that corresponds to f, but adds some random noise to the counts. And so then instead of releasing the exact counts, we release samples from these distributions. And the samples drawn from the output distributions, they should look epsilon similar to an observer. Okay, so that's the intuition. And we already saw the mathematical definition in the last talk, but here is the version that also includes the delta. So it says that for any outcome S that we might observe, the ratio of the probabilities on D and on D prime should be bounded by this exponential factor e to the epsilon. And then we also allow for some additive slack. But for the so our logic supports that, but for the most part, we're going to ignore that. And so small values for epsilon and for delta mean that the distributions are very similar, or very close. So they're hard to tell apart, so that means good privacy for us, so that's what we're trying to prove. So let's go back to Frank and see what happens to him. So we were looking at the cardio bin, because that's his category. And if we look at these noise spindles, we can represent that as a more familiar probability distribution on the right-hand panel here. And so the distributions that we're seeing here is exactly a Laplacian that's scaled according to epsilon, where the means of the two distributions are shifted by the distance between the inputs. So here they're one apart. And the idea of this differential privacy definition is that we get epsilon differential privacy if we can blow up the distribution on d prime by a multiplicative e to the epsilon and dominate the other curve. So that's sort of what's happening when we try to prove this differential privacy. Okay, so we know how to implement this. We have our histogram program, and we add some noise to the counts. We know that that's epsilon differential private. We just saw the curve that proves it. And we add the noise to all of the counts. So the final result is also epsilon differentially private. So we're good, right? Well, not quite. It turns out that reasoning about these randomized programs is very error prone. And in fact, a lot of the literature contains mistakes about mechanisms that people thought they had proven to be private on paper. And there's a lot of implementation bugs as well. And of course, our community has been working on this problem for a while, and there are some type-based approaches that offer high degrees of automation to mitigate this kind of mistakes. There are also some program logic-based approaches. And so they work well for, they certainly can handle this kind of histogram query. They also extend to more complex programs. But the fact remains that these things are tricky to implement and easy to get wrong. So people typically don't do that by hand. Instead, what they do is they use libraries. And so if you look at these libraries, they have some combinators that help you write these programs. And so one of the combinators that you find very often, that you find in any library that does this, is a privacy filter. And so this is sort of it's a higher order program that is parameterized by a privacy budget that you set in the beginning, and then you expose this try-run function that takes in a mechanism M, and if you still have privacy budget left, then you execute M, and otherwise you say, I'm not releasing any more data, and you stop. So this is a very useful construct if you don't want to do the privacy accounting yourself. There's another classic algorithm that you will find in any of these libraries, which is this above threshold. It was also mentioned in the previous talk. This is a building block for the sparse vector technique. And this one is parameterized by a threshold and then exposes a query function that allows you to execute a query and test whether you're exceeding a threshold until you find one query that is actually above the threshold. Right. And so I already mentioned this, but one thing that you'll notice immediately is that these programs are higher order. So they're both parameterized by another function, either by a mechanism or by this query function. They both also use local mutable state. And so the privacy filter in particular uses this local state to do budget accounting. So the privacy budget depends on the current state. The above threshold stores some randomized values in the local state, and it even does some dynamic privacy budgeting, where depending on the outcome of a computation, we might incur some privacy loss, or we might not. And so here we have a collection of complex language features that are so this particular combination of features is something that most libraries really require, but it's also beyond what existing tools were able to handle. So that was our motivation to develop ClutchDP, which is a relational higher order separation logic for proving differential privacy. And I've been showing you Python code, but really we work with more of an OCaml-like language where we support sampling from the discrete Laplacian distribution. We have higher order functions, arbitrary recursion, references, etc. And sort of the key idea that makes this logic tick and nice to use is that we represent the privacy budget as a separation logic resource. So you get one kind of privacy credits, the epsilon credits for the multiplicative slack in the differential privacy definition, and you get a different kind of resource, these delta credits, that track the additive slack. And once you have that, we also define a notion of Hoare quadruple. It's not a Hoare triple because we're relating two programs, so it's a quadruple. And under the hood, these are using approximate probabilistic couplings that have been well studied in this application domain. But we're adding some new tricks to that. And we also support reasoning about complex mixed distributions via pre-sampling tapes. So that was also something that was mentioned in the previous talk, that something like the noisy max mechanism can be difficult to reason about, and that's exactly one of the applications that we use these tapes for. And so using this logic, we were able to prove some nice reusable specs for a number of the building blocks that you find in these libraries. And several of them were beyond what previous work could do. And finally, yeah, so all of this is, of course, so the meta theory is, of course, formalized in ROC. Right. So how does this work? I already told you that the central reasoning device is this Hoare quadruple. And this just means that under the assumption that the precondition P holds and that E1 and E2 terminate with values V1 and V2, the postcondition Q should hold, right? So that's the central reasoning assertion for programs. Besides that, you get the privacy credits that I already mentioned in the assertion language and the full Iris toolbox. So you get the standard separation logic, you get impredicative invariance, you get higher order ghost states, including, for instance, partial heap ownership. You can use synthetic step indexing to reason about recursive programs. So it's quite an expressive setting. in practice, what happens with the privacy budget is that it lives in the pre and post conditions. We'll see an example of that. But before we get to that, one thing that's worth emphasizing is that we managed to set things up in such a way that all of the probabilistic part is isolated. So the assertion language is only probabilistic in the privacy budget. So if you're reasoning about a deterministic step in your program, such as writing a value to a reference, you just get the usual rule that you would expect for it. So it's quite that makes it quite user-friendly. Okay. Now, with this in hand, we can define an internal notion of differential privacy in the program logic, where we say that the mechanism M is differentially private internally if under the precondition that we have ownership of epsilon and delta privacy budget, we can show that the results that we return are equal. And so the way that you think about this intuitively is that we can use this privacy budget to pay for the discrepancies in the probability distributions. So when we do a sampling somewhere and there is a discrepancy, we have to give up some of this budget, and that in turn allows us to assume that we got the same observations. And so that's also part of the reason why it's enough to reason about the values in the post condition instead of ever having to talk about distributions on states, which would make this much harder to use. Right. Like I said, this is just a defined notion internally in the logic. So that means it's a first-class predicate, and it's very flexible. In particular, we can use the whole expressivity of Iris to reason about these programs, invariance, ghost state recursion. All of that integrates well. Right. We also have an adequacy theorem that actually gives meaning to this internal notion of differential privacy. So what that states is that if you can derive in the logic that a mechanism is differentially private in this internal sense, then it also satisfies the external expected notion of differential privacy. So the parameterized, randomized program that you get out by executing the program in the standard operational semantics is then also differentially private. And so this is just a sanity check that tells us that the internal differential privacy does what we expect it to do. Right. Of course, when you're doing data analysis, you compute several statistics. You don't just stop with one histogram. And the privacy credits support this kind of reasoning quite natively, quite nicely. So if your privacy budget, epsilon, is actually the sum of epsilon 1 and epsilon 2, so you can partition it that way, then you can split the resource into two separate resources that you can then move around independently and reason about, because it's just a first-class separation logic assertion. And so we can use this to reason locally and compositionally about the privacy budget consumption. And so one example that's quite nice, I think, is that the usual sequential composition theorem of differential privacy, for us, that's just a derivable fact. That's just falling out of our definitions. So if a mechanism is, if one mechanism is epsilon 1 differentially private and another one epsilon 2 differentially private, then if you run both of them on the same database, the result will be epsilon 1 and epsilon 1 plus epsilon 2 differentially private, and that's a very easy proof just using some of the credit yoga here. Okay, I've got to speed up a bit. Right, so I already said this is very flexible. And I want to show you quickly how you actually use these credits, right? So we saw the picture of what happens with the Laplacian. And so if we assume that the means of two Laplacians are at a bounded distance, and we have the corresponding c times epsilon amount of privacy credits in our precondition, then we can conclude that the results will be equal. And this is, again, proof by picture. But if we define adjacency to mean that the inputs are actually C-close, then this just tells us that the Laplacian is internally differentially private, just as we would expect it to be. Okay, so this is old news, but it works nicely in our setting. What's new here, for instance, is this other rule for reasoning about the Laplacian, which works by partitioning the outcomes according to some threshold t. And then depending and we get two different post conditions here, right? There's a disjunction in the post condition, which is interesting. And so depending on how the left-hand side sampling goes, if we get a value, z, that's below the threshold, then we don't have to spend any privacy budget, because we assumed that the inputs are close, so the right-hand side program is also going to sample something that's below the threshold. But on the other hand, if we are above, then we can pay the budget, give it up, and force the right-hand side program also to be above its threshold. And so this is inspired by some previous work as well. The above threshold is where we use this particular rule. So again, we take a threshold parameter t here, produce a noisy threshold, and then we construct this closure f that takes in a query parameter q as well as a database. Whenever you run f, you evaluate the query on the database, you add some Laplace noise to it, and you compare it to the threshold. And what you want to show is that this is a differentially private program. And so we can give this a nice specification that completely abstracts over the internal use of credits, where a client only has to know that it has to manage the authorization token that tracks whether or not we've observed a value that exceeds the threshold. And so this really follows sort of the operational picture of this algorithm. And yeah, so with that, I invite you to look in the paper if you want to know more about the applications. We did a number of standard constructions that you will find in these libraries. And if you're interested in how the logic works under the hood, I recommend that you read the full version, which has a bit more details on how the judgment is actually defined and how the new choice rule is proven. And with that, thank you for your attention.
Okay, thank you.
We're hiring, of course, so yeah.
All right, we have time for some questions. I said 0 minutes, but I lied. We have around 1.5 minutes left.
Okay.
Yes.
Hi, good talk. Thank you. At least the part that I've seen. So I have a question. You said, so you have a result about adequacy where you relate what you prove in the logic to the usual notion of differential privacy. Yep. Could you say something about the other direction?
Yeah, we're writing that up.
Oh. So you have a result in the other direction,
yep.
But it's secret.
It works.
So
we're writing it up. It's not in this paper, but yeah.
Okay. All right. Thank you.
A couple of weeks ago, I managed to prove that it's complete. Yeah.
Any more questions? Okay, I have a question. So it's known that these Laplace mechanism can be subject to floating point attack. Is this something you've thought about or looked at verifying?
So we're actually working with the discrete Laplacian distribution,
yeah,
precisely for that reason, because nobody in their right mind should be using floating point implementations. Of course, all of the libraries use floating point implementations, but there's also been some recent work on certified samplers for these discrete distributions that we're hoping to integrate with. And I think that's, well, the floating point implementations, they're not private. So you really should be using the discrete ones.
Makes sense. All right, let's thank our speaker one last time. So that's the end of the session. Thanks everyone for joining, and we have a coffee break outside next.
It's up here.